So once again, good morning, everyone. Good afternoon, depending on where you're joining us from the world. I would like to welcome everyone to Harmattan School. This is the 5th edition of the Harmattan School. And my name is Victor Ekpo. I'm Secretary General of the Nigerian Association of Medical Fields, and I'll be co-moderating today's session alongside Favor. Favor, please, can you say hi?
Good morning. I'm Favor Matayo, a medical physics intern at Aberdeen Royal Infirmary, Scotland. And I'm happy to join you today. I'll be hosting with Mr. Victor, just as I said earlier. Welcome once again to Harmattan School 5.0. The Harmattan School is a flagship academic and capacity building initiative of the Nigerian Association of Medical Physicists, designed to introduce undergraduate students to early career professionals to the exciting and impactful world of medical physics. Since its inception in 2021, the program has grown into a vibrant learning platform, attracting thousands of participants from across the world. And it is proudly endorsed by NAMP as part of its mission to promote education and professional development in medical physics, to inspire the next generation of medical physicists, and to bridge the gap between theoretical physics and clinical applications. So this year's theme, which is the physics of lasers, ultrasounds, and more, explores how the core principles of physics powers the modern technologies, from ultrasound to lasers to emerging innovations shaping the future of healthcare. You're welcome.
Okay, so thank you very much, Favor. And before we begin, we'd like to have a few quick reminders. We'd like to please remind everyone to keep the muted at all times, and because there are lots of people in the meeting, so it will be distracting if you're trying to speak above anyone else. You're also encouraged to drop your questions in the chat box during the lecture. Questions will be addressed during the Q&A session at the end of each lecture, and you're also you may also be invited to ask your question live. And before I forget, there might be a post-lecture quiz, and this contributes to your participation and certification. So, having said that, without any further ado, I'd like to introduce our program coordinator and president of the Nigerian Association of Medical Physicists, Dr. Iyobosa Blessing Owadie, for our opening remarks to the Harmattan School 5.0. Dr. Iyobosa, please.
Thank you. You just called all my names. Good morning, everyone. And thank you. Just like our moderators have said, we welcome you to the 5th edition. Last year, we couldn't hold the school, so it should have been the 6th one, but unfortunately, we couldn't hold the school last year. So I just want to say two things. On behalf of the Nigerian Association of Medical Physicists, we welcome you. This is not just another webinar or another summer school or there are lots of webinars and summer schools that are being held, all over the world by different societies. For us at NAMP, it's a strategy. We are trying to address the issue of shortage of medical physicists in the region, in Nigeria, in low and middle income countries, generally speaking. So the whole idea is to get, so the original targets of this school were undergraduate physics students, but over the years, we have seen that we have gathered interest from postgraduate students and even practicing medical physicists. But the whole idea is to get us to appreciate and see the different areas physics is applied in medicine. Beyond the regular, most people think of medical physics only in terms of radiation therapy, nuclear medicine, and diagnostic radiology, but there are several other areas physics can be applied in medicine, and that's what we've been trying to do every year, to introduce us to different areas of medical physics, with the aim that at the end, we will be interested in taking up careers in medical physics. So we are hoping that at the end of these 3 days, if you are not considering a career in medical physics, you will start to consider a career in medical physics. And then finally, if you noticed, so we have been partnering with IPEM, which is the Institute of Physics and Engineering in Medicine, for the past 6 years. And if you notice this year, most, if not all, our facilitators are from IPEM. And that's because the topics we are considering this year are very specialized courses, and we do not have experts in the country that can take those courses in the country and even around in West Africa. So this is also another big issue. So we're hoping that, like I said, at the end of these 3 days, we'll get medical physicists to start to look at areas like, lasers. Dr. Paul is going to tell us about that this morning. Robotics, prosthetics, rehabilitation, phototherapy, and ultrasound. These are areas you don't really find physicists in, especially in Nigeria. So hopefully that will be done. So once again, I just want to thank every one of us. Those are old and returning Harmattan School attendees, the new ones, and all our facilitators that will be joining us for these 3 days. Dr. Paul, Dr. Kuma, Dr. Keith, Professor Praminda, and Dr. Lucas, and other panelists that you will see along the way. So once again, thank you, and I hand over back to our wonderful moderators. Thank you.
Okay, thank you very much, Madam President. What a wonderful time to be alive. I think it's also my first time of hearing about lasers as something that medical physicists are interested in, and to find that they're even specialists in it, and they call themselves medical physicists and not any other name. So it's a very fantastic thing that we are beginning to feel that. I'll just go through what the program for today is, because this is going to be very, very loaded couple of 3 days. And we're going to be having 3 lectures today. I'm sharing my screen now, if you can see it. We are going to be having 3 days of practical, life-changing medical field discussions for everyone. Today is mainly about lasers, and we have 3 lectures between the hours of 9 to 12 noon Nigerian time. And then tomorrow as well, the same thing. We're going to have the same different lectures on sound waves between 9 to 12. And then for what we call, for the day after tomorrow, in Nigeria, we call it next tomorrow. For next tomorrow, we'll also have 3 lectures on other aspects of physics that are very interesting and that I'm sure that everybody will benefit from. So without any further ado, the lectures are about to get started, and I'd like to invite my co-moderator to read the short bio of Dr. Paul Deacon-Smith, one of our Nigerian brothers by extension. Favor, please.
Thank you, sir. So today we'll be delving into lasers and clinical application of lasers, just as Mr. Victor has said earlier. And our first speaker for today is Dr. Paul Deacon-Smith, and he will be introducing us to the basic physics of lasers in the first session. Dr. Paul Deacon-Smith is the Principal Radiation Safety Officer, Laser Protection Advisor, and radiation instrument at Guy's and St. Thomas Hospital, London. He's in charge of training and issuing laser certificates at Guy's and St. Thomas Hospital, London. For any surgeon who is starting to use lasers for the first time, he has 20 years experience in training surgeons and medical staff on laser physics and safety. We're excited to learn from your expertise, sir. And so this is just to everybody. Please ensure your mics are muted all through the sessions. And if you have any questions along the line, you can just put them in the chat section and we'll answer them during the Q&A section. Dr. Paul, you may please begin when you're ready. Thank you very much.
Oh, great. Thank you very much. So just to introduce a little bit more. So I've been doing this for roughly coming up to 26 years now. So I've been in it a bit of a time, yeah. And I also used to respond to laser calls. So for example, if there was a problem with a patient on the bed, I'd go along and see if we could get the laser going, which would prevent them being sent home, because medicine is kind of funny field. You know, you patients coming with the hope of getting treated. So, you know, the one thing we have to try and do is to actually treat them. So we used to do that. We still do that, as a matter of fact. So I just wanted to make clear that when it comes to lasers in medicine, generally medical physics, we don't look to design a brand new laser. We can do that, but we work in conjunction with the universities, and most hospitals will have a university attached to them. So in our case, it's King's College London. And so if there's going to be any research on lasers, the school will do that part of the business and typically would work alongside clinicians. Primarily in medical physics, when you're dealing with lasers, what you're concerned about is the safety of lasers being used in the environment, okay? So you'll have your clinician or your operator who's a doctor, and they're going to use the laser. You may have some clinical nurses who are trained to use the lasers on, as you know, for treatment, particularly like in places like dermatology. But as a medical physicist, your job is to ensure that that equipment is working to the manufacturer's spec. And so what you'll do is that you'll do audits, annual audits. And in our case, we go a little bit further. We get involved with the purchasing to make sure like the laser is not some piece of rubbish that is going to break down. Yeah. So you're looking at it long term, what the costs are going to be, because there is a limited budget when it comes to equipment in any hospital. So you're kind of like a guard of the system when it comes to the equipment coming in and looking after it. Okay. So that's kind of like what it is. And my talks you'll see today is mainly explaining a little bit how the technology work. You garner more as you go along in time in the job. Yeah, you'll find yourself specializing depending on how they use the lasers. I'm fortunate to work in a center where there's a whole host of it. When I first started all them years ago, there was only 3 departments using it, which was dermatology, plastics, and theaters. Now lasers have just grown. It's like in everything. Even physiotherapists are using lasers, and it's really incredible to see how, as a tool, it's being maximized and finding its way, and there are different applications for it. Current research that I'm involved with the people from King's, they're now coming up with lasers where instead of having to take biopsies, they can use the laser itself to determine if there's tissue that is cancerous, for example, orally inside your mouth and things like that. So the field of lasers is growing and its uses are just expanding. It's unbelievable. Okay, so we're just going to go through the basic science to begin. And I think this is always good because this is part of the courses that we do. So we do courses for MSc. Sorry, I can hear some voices. Yeah. Yeah, so we do courses in the university for the scientific students coming through for medical physics, and typically this is the what would I say? This is basically the course material that we would use. We do not go into deep physics because as a medical physicist, you're not going to be required in your daily activity to be designing lasers, but you need to know how they work somewhat. And so this is basically extracts from the courses that we teach. And I hope that with the 3 of them today that you will get a really good idea of what we do. So I'll just continue. Okay, so these are learning objects. We get an idea of what a laser is. We'll have a look at the spectrum and essentially the things on this list, but we'll go through that because I think time is not on our side at the moment. Okay, so the laser is an acronym. It's just basically the letters for what it actually means, which is light amplification by stimulated emission of radiation, right? And it's a device that generates or amplifies coherent direction and monochromatic light via the process of stimulated emission. So if we look at what a light source is, for example, a bulb, the light emitted from a bulb is going in all directions, and generally they're not in phase. But with a laser, when the light that is manufactured are all in phase. So if you think of frequency where it's going up and down, all the light are going down, up and down in tandem with each other. And that's the one property that separates laser light from all other light, okay? Okay, so here's a spectrum. And I like showing the spectrum. So for example, are you able to see my mouse? Sorry.
Yes, we can.
Oh, brilliant. So this is the entire electromagnetic spectrum. And so if we look down here, there's radio. For those of us who can remember the days of radio, there's a lot of people who don't know what a radio is now because we have all these electronic devices. These are really long waves, and they will stretch for miles, you know, and so that's the bottom end, the weaker end of the electromagnetic spectrum. Then we go into microwaves. Microwaves are actually a point to note. Microwaves were the first laser. It was known as a maser. So the first laser ever made was a maser, and it was done with microwaves. And it was to test the theory that they could produce coherent light. And so microwaves are typical of your mobile phone, your microwave ovens, and things like that. Then we go up to infrared. Sorry. Infrared is like heaters. It's just beyond the visible light spectrum. It's a weaker end of the light spectrum. And you will see, for example, that we do use lasers within that part of the spectrum. Then we have visible light, which is typically what we see with our eyes. And there is a limit of visible light, but you'll find that most of the lasers that are used in medicine are visible. And then there is ultraviolet. Again, this is stretching at the other end of our visible spectrum, and we do lose a couple of lasers in that area. We'll come on to that later. And then after that, you get X-rays, which of course we use to see through the body because these rays are much more energetic, and as a result of that, their wavelengths are much smaller. And then finally, you get like gammas and cosmic. Gammas are typically used in radiotherapy. The beams that we use are on the order of anywhere from 8 MeV to 20 MeV machines. And when I say EV, that's how we measure the energy in a photon, which is what makes up the electromagnetic spectrum. They're all photons. And so typically it's 1 electron volt is 1 electron being pulled through 1 volt. And that's the energy that is involved here. And so when we speak about energy, that's kind of the reference that is used in science for that energy level. And then of course there's cosmic energy. Another part of my job is that we calibrate in a secondary standard lab within the hospital all radiation instruments belonging to the hospital, belonging to the school, and we also do it for many other hospitals. So it's a kind of unique lab in a way. There's not many in the country. And part of my discourse with respect to that, because we also teach that, is to let everybody know who are scared of radiation that your body, over the period of a year, every cell in your body would have been impacted by at least 1 cosmic ray. So we're constantly living in a radiation environment. And so radiation is not anything that is new to the human. And anyway, you can see my list below here, where we have ultraviolet, 200 to 400 nanometer, where we use a excimer laser, which is 308 nanometers. And the thing with that, which we'll come on to later, is they don't penetrate deeply, and that's very useful in terms of what we use it for in the hospital. Then you have your visible range, which is 400 to 700, your near infrared, 700 to 1400. And just to note that these are the things, these 2 ranges, this visible and near infrared, will make it to the back of your eye. So we consider them highly dangerous when it comes to work and require PPE to protect your eyes. And then after that, of course, you have your middle and your far infrared, but we'll touch on that. So how does it work? Well, this is originally a good description of what a laser is and how it works. Of course, now we have semiconductors and they're slightly different. They're produced by using PN junctions and having ways of getting the beam out. However, this is generally the system here that you see here is the standard for most lasers that you will come across. And so to explain it, you have a cavity, which is your cylinder that you can see here. There are 2 mirrors, 1 at each end. One is a completely 100% reflecting mirror. And on the other end, there's a partially transmitting mirror, which means it lets about 5% of the light within the cavity out. So lasers are highly inefficient. That's another thing to note. And then any material, you can literally lase any material, even the things that may not look transparent to us, may be transparent to the energy that is being produced. So we can use solid, liquid, gas, vapors. It's really amazing. And now they have things like plasma lasers. And basically, what you have is that you have your lasing material inside of this cavity. And then what we're going to do is that we're going to excite that material, and we're going to cause the electrons that are within that material to jump up many levels. And then when they collapse, that's how the light is produced. Now, once we do that to the material by exciting it, and the light is exiting the material, it will bounce around with these mirrors. In bouncing around, there's a little unique property that it does, which is to trigger. So each photon will trigger another photon from the material. So now you get two. And that's basically where the amplification occurs. And we'll talk about that later. So the other thing about our laser is we need a beam delivery system. So we'll have to attach something to it. We'll have a little look at that too. And your energy source. Energy sources can take two forms. It can be a huge flash lamp. Well, when I say huge, I mean very powerful. I mean, you wouldn't want to be in a room if that flash lamp went off. They're huge, bright, very bright. If you were to think of your mobile phone with a flash on it, and you were to put that up to your eye, you can imagine how blinding that would be. Well, that is exactly what would happen in the whole room with one of these flash lamps. And they're typically high voltage. They'll run anywhere between 1,000 volts and 5,000 volts, because you're going to dump a lot of energy across a gas, which is typically one of the rare gases, which is like argon or krypton, very neutral gases, so they won't react with materials around them. So you'll always have it as a constant gas. And that's the kind of materials that we will excite to produce the light, which is going to be the exciting energy for your lasing material. Okay, so that's typically how it works. Another thing that is particular about these mirrors in the laser is that they're not they're what we call first surface. They're not rear surface. So in the morning when you get up to go to work, what you'll do is you will look in the mirror to make sure that you're presentable to the world as far as you're concerned. But that mirror that you're looking in is a rear surface. That means the reflective part of that mirror is on the back part of the glass. It's not at the front. Well, we can't use that in lasers because then you get that anomaly that comes into play, which is the index of refraction. And that will change the beam's orientation. It won't be bouncing in the right way. And so what we do is the coating is on the front of the mirror. We use very special coatings, and we have to also put another coating which prevent that coating from oxidizing. And so that is why we call them first surface mirrors. The reflecting area is on the first surface of the glass and not on the back. Okay, so this is what it's about. It's about absorption, stimulation, and emission. So this is just a rough example of how the system works, where it absorbs energy and it goes up a level. From the inner core, it goes up. And then when it comes back down, it releases that energy. And then you can see as it goes along, it will stimulate an extra photon, so there becomes two. And that's kind of the amplification process. Just as a point, typically when we have systems that are working, the electron won't jump one level. What we'll do is that we'll jump one huge level, and when it comes back out, there'll be an almost immediate collapse to another level, which is not the ground state where it came from. And then there will be a further collapse of that electron back again down, which will be the lasing level, which is a much slower process than the first level. I know it's just how they work, and typically they're very well demonstrated in things like dye lasers. Okay, so we have the absorption, which is when the electron transits from the lower energy level to a higher one, which is what I was explaining. Then there's a spontaneous emission where the electron spontaneously emits a photon to transmit from a higher energy level to a lower one. And then you get your stimulated where the photons are bouncing around and stimulating other photons. And that is basically the explanation of a laser, roughly. So here's an example of the population inversion. So when we excite our electron and it goes up, it leaves the ground state and it goes into the excited state, which is this transition here. Okay, and then you can see what I was talking about, which is there's a fast reduction in levels by the electron, and then there's a slower collapse of the electron back to its original ground state. And this is where our lasing light is produced, not here, because this is just it collapsing back to a more reasonable state. And typically that reasonable state will be guaranteed by the environment because of the energy that you've put in. And so this is how it works. So we can use optical pumping, electrical pumping, we're using a voltage source and a huge electric field, or chemical pumping, which is a reaction. So with reactions, you're basically changing the state. But again, this whole process here is called pumping. So here I put in a picture of what a typical gas laser will look like. This is a helium neon laser. You'll typically see them, they're long little tubes. They're often used in the main laser as an aiming beam because the clinician who's doing treatment will like to know what area they're treating. And so with a lot of the lasers, there'll be a little red or green dot that comes out of the laser, which will be this laser, to point as to where the main laser is going to hit. We also use helium neon lasers as pumping lasers. So sometimes you have two lasers in one. One laser will be pumping another laser to produce a different laser mechanism, which is probably a really fast timed laser. So like things like pico lasers and femto lasers. So, but that's what we call mode. We'll get onto that. So you can see here where we're using the voltage is going through and we are exciting the gas to do the discharge. Our mirrors are at the end and then we produce the light. These here at the end are your mirrors, and that white light that you can see in the middle here, that very fine beam, is your lasing light. That is a light being produced in there, which will produce, which is actually the lasing occurring. And this metal thing is a shield. Here is an example of an electrode. So they're quite simple mechanisms when you look at them like this. But the whole idea of the electronics around it to guide it and to create it is quite complex. And like I said, highly inefficient. So some of our main lasers have cooling systems on them, which is like, if you look at it, it's equivalent to a car. They have radiators, they have waters running through, everything to keep it cool. So they're highly inefficient. Here's some examples of the mirrors. And these mirrors will be coated with material which will be tuned to the wavelength that that laser is made for. And so you can see here examples of the colors. And here we can see these are the lasing centers with the points where the light will exit. So it's not a lot. All this here will have reflections. And this is a point where in that non-100% mirror, they will be escaping through. So it's not a lot of the light that is allowed to leave. So having produced our laser, we need to deliver that light. And we have to get that light out somehow. So there's two main means of doing that. And so in our first instance, we can use fiber optics. And fiber optics are really clever stuff. I'm always intrigued by the fibers I come across, because when you look at them, they look like very fine plastic threads. I mean, you know, you can see here, you have your, like, typically what would be used for Christmas lights. But like with the ones that you're going to use, because we use fiber optics that go inside the patients, and they have to be small because, you know, you don't want to be creating large holes in patients. but the technique behind fibers is really clever. So they're not plastic. They're probably coated by plastic, but fiber optics are typically glass. So what you have is one glass inside the middle and another glass that wraps around that glass. And the whole idea is that these two glass have different index of refraction, okay? So they bend light in different ways. And in the case of the fiber, you choose a different kind of glass that is going to cause what we call total internal reflection. So as a result of the way the light is being bent in the glass, we get the light traveling all the way down the fiber till it comes to the end. When you're using some fiber lasers, for example, in dermatology, they have a few, which is the dye lasers. When you do a flash or press the button, there will be a slight flash along the fiber, but it won't be enough to cause a problem to users outside. Because not a lot of light escape, just some. But the main core and energy is transmitted down the fiber itself. So that's how they work, and it's really clever. And so that's one means of delivery. The other means of delivery is by an articulated arm. So for more powerful lasers, for example, your CO2 or some Q-switch lasers like the ND-YAG, used to be like, I think the first ones were the ruby lasers, but they're not used so much anymore, which was 694 nanometers in terms of wavelength. Excuse me. So what you have is a principle of basically like what you see in the submarine, where they put the thing up to look above the ocean. You have your mirrors inside your arm, and they're all first surface mirrors. And the beam will go along and is bounced around until it gets to the end. So that's typically what an articulated arm looks like. And at the end here, where you see the port, they will attach different handpieces, which might have lens to either give you a larger beam or a smaller beam, depending on the use. Okay, so alignment tends to be a problem. So one of the things that we do is, as part of our test, is we will stretch the arm, fire it onto a piece of paper, and we will have marked the point where the aiming beam is dead center to, or like a cross. And having fired a laser, we look for any difference, any wandering of the main beam away from what the aiming beam is showing. Now, we will normally use plus or minus 3 millimeters for that. Anything outside of that, we will want the engineer to come in and adjust the mirrors, because it means that the mirrors may have been misaligned because somebody's knocked the arm or something. So these are the things that we kind of look out for as physicists when we're checking the kit. So the properties of laser light. Okay, we're going to look at the prop now and see what separates it from regular light. So it's monochromatic, which means it's a single wavelength, okay? And that's why a laser will have a particular wavelength. For example, a CO2 laser will be 10,600 nanometers. We can use a dye laser, which might be 595 nanometers. You also get like lasers which are used both for eye and other uses, actually, which would be 532 nanometers. ND-YAG will be 1064 nanometers. So that's just examples of some of the laser light. However, nature is never kind. So however much you would like something to be ideal, it never is. So what you'll get is a very small spread of light that is being produced. We can never predict where an electron will start from and where it will end. And as a result, that's the kind of photons that it will produce. It won't be far off. So we're looking at probably just a few nanometers. But your main energy will be at the energy of that is specified by that laser. And here's an example of coherent, which is what I was talking about. They're all in phase. And so if we think about the electromagnetic waves in this way, then you can see what we mean. They're all in phase. They're not scattered in every direction. They tend to be true to polarization. So if you're using polarized sunglasses, for example, the laser light will go through in one way, and if you turn your glasses, it won't go through in the other way. And that's typically how the light behaves. It's all coherent and operated in the same mode. It's highly directional, and that's something about lasers. So one of the lasers we have, for example, is CO2. That will go, because we're right by the River Thames, it would literally go across the River Thames without much spreading. And the light will be in a nice narrow beam. And so you can imagine we can keep the power going for a great distance. There will be some spread on all lasers. And if you're using lasers from a fiber, that will spread really rapidly because it loses its coherence as it goes down the fiber. It typically comes out, and it comes out as an angular beam. And so generally all fiber lasers would have corrective optics. But when you're producing down an arm, it will be much more directional and in a narrow beam. So the other thing now is we've produced the light, we're delivering it down our source of delivery, which is the beam, which is the articulated arm or fiber. But we need to know how we're delivering that laser. And so the other means of delivering that laser, we want to know, because we need to know how much light we're going to use in a treatment. And so we look at it in this way. We have a continuous wave, which is if you press your handpiece or your foot pedal, the beam will just stay on and it will just keep going until you release. And so that's known as a continuous wave. There's also a pseudo continuous wave that is anything greater than a quarter of a second. And there's a reason for that. Pseudo continuous wave is only applicable to the visible range. And the reason for this is if somebody was to shine a light in your eyes, you would instantly respond, and that is called a blink reflex. And the typical average response when you look at someone who's young versus someone who's old, we take all those responses and we do the average, is a quarter of a second. So it would take a quarter of a second for you to totally close your eyelids in response to having light go into your eyes. So when we're doing safety measurements, we consider that as a continuous wave. It's almost as if somebody is shining a light at you constantly. And so when calculating out safety aspects and guards against that kind of light, we have to bear things like this in mind. This figure comes into it. Then you have your pulse. That's typically from 10 microseconds to 1 second. Most of the lasers you find in medicine are going to be within this range. They're going to be pulsed. And pulsed laser can occur because each laser light has to be produced by a pulse of energy in the cavity, or it's shuttered. So for example, gas lasers are more continuous lasers because it's just an electric field which is constantly on, which constantly excites the gas. And so the cavity is producing the light nonstop. That is typical of things like CO2s. If you wanted to turn it into a pulse laser, you have to introduce a shutter where you interrupt the beam. So you're going to chop the beam up into bits. And so shutters are used there. And so this is what you get in shuttered outputs. Never that ideal, of course, because nothing is ideal in nature. And then there is your Q switch. And this is another type of output. Q switch are very clever. The thing with Q switch is, if you think of the energy in this area, which is in your pulse here, what you're doing is instead of letting it out immediately so that you get this lasing effect over this period of time, what you do is that you keep the energy bouncing around in the cell, or you can keep all the electrons in a state where they're all standing up in their energy levels. And then at the last minute, you let them out. And that's why you get this shorter time period. Now, this is really good because what you're doing is the total average energy that is in here is also going to be expressed in this pulse. So we're looking at 4 to 40 nanoseconds. However, in our modern use, we no longer have these long times. What we are using is 4 nanoseconds, okay? And so you're talking about all the energy that will be delivered here is going to come out in a very short period of time. And that means your peak pulse is going to be much higher in amplitude than your regular pulse. And that's quite useful because explaining why Q-pulse is very good here. If you're using a laser on somebody's skin or in their eyes, you don't want to hang about for a long time. And the analogy I normally use is boiling a kettle. If you turn your kettle on to boil the water to make some tea, it takes a while. The energy that you put it in, if we assume a value and say 1 kilowatt, which is kind of low, but say your kettle is 1 kilowatt, it may take you a couple of minutes, 2 to 3 minutes before your kettle is even beginning to boil. And that would be in your pulse. It's delivering the same amount of energy over a period of time. Now, just imagine that you had a kettle where you could take all the energy that you were putting in over that period of time, and you were to suddenly put it into your kettle. Then what would happen is, literally, your water would immediately evaporate because it's so much energy that it just can't hold it. So it would just have this great big explosive evaporation. And that's the principle of our Q switch. So what we want to do, and the other thing about it is, heat is a time-related effect. So your water didn't boil instantly. It had to take, as it accumulates more and more energy, it gets hotter and hotter and hotter. So we know that heat is a time effect. However, in delivering this energy really quickly, we can do a lot of damage, highly explosive damage, without that major heating effect. And that's really good. So, for example, if we wanted to bore a hole, then we could bore a hole in a very small area and do the job really quickly. We're talking about nanoseconds. But at the same time, it wouldn't heat the tissue around it because it hasn't spent time enough for the heat to expand through the tissue. And so that's the beauty of a Q switch. So uses, for example, with Q switches are tattoo removals. When people have tattoos and we want to get rid of it, we literally want to go in and blow up the ink that is within the skin, but not heat the skin. Another good use is hair removal. And of course, a really good place to use it without causing tissue because damage, we don't want to damage the tissue, is your eye. So most eye lasers, when they're doing work, will be Q switched. They'll be really fast response lasers that will go in and do the work that the optician or the ophthalmologist needs to do without damaging the nice surrounding transparent media around it, the gel of your eye. And so that's the beauty of Q switches. So we'll move on. Okay, so here's the typical lasers found in medicine. We have gas lasers, CO2, which is a very popular workhorse. CO2s are fantastic in that they don't penetrate deep into the skin. They're very surface level working because it's a very long wavelength. And they can be collimated. So you can put lens into the beam and bring it down to a point in which it then becomes a fantastic knife. So surgeons can use CO2 to cut things. So like, for example, keloids on your back of your head and along your neck and places like that, typically we'd use a CO2. Because if you use a scalpel, there's a lot of blood and there's a lot of having to use a vacuum suction device to get rid of the blood as you're cutting away tissue. However, with a CO2, you can cut, because at the same time it's cutting, it's cauterizing the tissue, which leads to a lot less blood loss. And so that's the beauty of using a CO2. A very handy tool, can be used for so many things. And it can just take layers of skin. So you'll also find CO2s in beauty clinics, where they will use it like on your face and places like that, where you, what they call, do a facelift. So it will take off a layer of skin, which is very thin, leaving behind your new cells, which is coming out. So you can see why it would be popular in places like beauty clinics. And so, of course, you got helium, neon, and argon, and so on. You got your vapor, which is metal vapor, copper, gold, manganese, and so on. So you excite it by heating the metal to their vapor state and then applying high energy electrical pulses. We don't use that. There was one that came in on the trial, but I didn't feel like it was a safe enough instrument to have, because I just felt there could too many things could go wrong with it, so we didn't implement it. Then you have your liquid lasers. A lot of them lasers are liquid in places like dermatology. So these are organic dyes in solution, either water or solvents, and we excite them using very high-powered flash lamps. And it's basically the dye molecules that they're excited and give out their characteristic color, which is that wavelength that we want. Solid state, so your ND YAG, ruby, and erbium YAG. So these are crystals or glass doped with rare earth and transition metals. They're very good. These are the lasers that actually scare me, to be honest. They look so simple. If you see the crystal core of it, there's some of them are just like 1 centimeter by 1 centimeter cubes, which you're going to excite. But these are the lasers that I always find that will put holes in things. So in my measuring instruments that I go along to check the output, with these guys, I'm always very careful. I always try to ensure that they are not at a point, you take them off axis, the beam off axis, so you try and get a bigger beam so that they don't bore holes in your measuring kit. And then, of course, you have your fiber. So these are rare earth elements, which will be doped in your glass fiber. And by pumping light down these fibers, it excites these rare earth minerals here, and produce its own light, which is also transmitted along the fiber, and then you get it out. So they're typically excited by pumping using other diode lasers. And then, of course, your semiconductor lasers. These are growing in use because as a semiconductor technology gets better, they're now able to produce a lot more wavelengths. And so you're now getting blue wavelengths. I've seen wavelengths coming out which is bordering on the UV, and they're very stable. So once you start producing the light, you generally get continuous waves, and you can literally they just happen to be the most reliable lasers that I find around at the moment. They last long. We have them for years. They hardly go wrong, and I think they're really brilliant. And I really hope that they continue to expand this field. And then, of course, your Q switch, which is what we were talking about earlier. And so these are like basically the different types of laser you'll come across in a medical environment. So this is the end of this talk, and I just wanted to show you a picture of what a real laser looks like. So this is one of the guts of a laser which we took out of service, and I just wanted to show you. So in here is a laser cavity. So along there is a laser cavity, and along here will be the flash lamp, which is why you see these very powerful leads. And this one will be high voltage. This will typically be 2 to 5,000 volts that we will put in this flash lamp, which will excite this cavity, which will go along. And this is the pathway that you can see here of the laser, And here is your shutter mechanism. So this it's just an electronic shutter. You put the pulse across it, it will move out the way and turn off the beam. And here is a helium neon laser, and this is your aiming beam laser. So this aiming beam laser will always be on. It will bounce on this first surface mirror here, and there's a hole on the side here where it will go through and it will follow the pathway. And so what we'll use here is a glass that is basically a two-way mirror, and it'll be part of the system. It will go in and hit that mirror and come all the way through, and that beam will always be on, because in this shutter right here, let me just show you, in here is the lens, which acts also as a mirror. So this lens, while it's keeping the beam inside without letting it out, will allow the other light to pass through. So that's quite clever optics. So it allows one light through, but it doesn't allow another wavelength through. It will reflect that wavelength. And so that's just using clever optics to do that kind of thing. Here is an example of the cooling port. This is where the water will come in and then it will exit at another point. And that is, this whole system here will be flooded with water, and it will constantly be pumped around through and then enters out into a radiator where it will keep this whole system cool, because it does get hot, believe it or not. So this is a typical ND-YAG Q-switch laser core, okay? And this shutter system is part of the retarding system. So once this shutter system moves out the way, the light will escape. But once this stays in, this light, this lens here will keep the light that is bouncing around slightly off axis so that it cannot actually totally laze and lose its power. So what happens is the light is kept in a state where it's continually being excited, and its excitation is being kept up for a period after the flash lamp has gone off. And so that's typically what the guts of a laser can look like. Of course, you get different designs and so on. But generally, we do not get involved in that as medical physicists, because it's not our job to either try to fix them or to do anything like that, even though for years I've got involved with fixing them and looking after them. It's not typically the job of a medical physicist. And I also, as part of our safety lectures, ensure that we tell the staff they do not open the laser, because there's a huge risk of being either electrocuted or with that lamp going off in their eyes and them being blinded. And so that's it for this talk. I think we have 2 more to go. How do I get out of this?
Yes.
Okay.
Thank you very much, Dr. Paul Deacon-Smith. I hope I'm being heard.
Yes, I can hear you quite
lecture.
clearly.
Yeah, fantastic lecture. Looks like a very interesting part of physics to go into.
So I hope that, so
there
just
are
a
lots
point.
of questions.
Yes, I can take
box.
any question.
Yeah.
I hope you get to pass the.
Okay, great.
I hope you get to pass on the PDFs to the
there
people.
are lots of questions in the chat box.
Okay, let me find the chat box. Okay, cool. So.
Yes, we can do that. If that's fine by you.
Somebody has their hand up?
Yeah.
Please, go ahead.
If we can send it to us via email, we'll send it to all the registrants.
You're breaking up. You're breaking up.
After the lecture. Okay. Favor, I believe you were taking notes of some questions.
Thank you so much, Mr. Victor. Can everybody hear me clearly, please?
Okay.
Yes.
Okay, thank you, Dr. Paul, once again.
Go ahead, Favor. Please read out the questions in the chat box.
All right. So some of the questions are closely related to what our other two sessions would be on. The
Okay.
first question, yeah, one of the questions is related to how the lasers interact with the body and then the clinical applications. So I would suggest that we move to the next session and then we can answer these questions if the participants are still not fully and well understood on the questions. Would that be okay, Dr. Paul?
Oh, that's fine with me. We can do this anyway. I've put aside this day for you guys, so that's not a problem. I just wondered if there were any questions on the physics of the laser, or anything like that. It's fine if there's none. We can just move
There
on.
were some questions on the physics.
Okay. Well,
You can
well,
take
let's
those
let's
ones.
deal with them. We can go through it. I don't mind. It's easy to get on to the other talk, So
Okay, so I have a question here, and
yeah.
I'm just going to read it out. Under
Okay.
the ex on, this is a question by Evie Oyeto. I hope I'm pronouncing the name correctly. It says, under the examples of lasers, we have a semiconductor laser. Can you
Yes.
please explain how it works? A
Oh,
semiconductor laser.
sure. So if you did any kind of electronics or anything like that as part of your physics, you'll know that you have a PN junction. And so PN junctions are quite unique. So we use them to make diodes, things like that, which is why it's called a diode laser. Now, a diode is a semiconductor device which basically allows current to go one way but not back. And it does it by once it's using the idea of holes. So some of the materials will be lacking in electrons in its outer band, and some will have extras in their outer band. And by merging these two materials and having a little middle bit fusing those materials, what you get is a kind of transmission band where when the electrons are coming in, they will fill the holes in one direction and so prevent current going along. Or in the other direction, if you have the current going the other direction, they will just keep on going. Now, the beauty of that is they have energy levels in semiconductors. And so basically what you're taking advantage of is those energy levels, what we call band gaps. And with the band gaps, when we excite the band gap, your electron will go up to a certain level and then it will collapse. So typically diode lasers will use an electric field to do the excitement of the electron, which will jump up, and then when it collapses, it produces this light. So they will create small channels in that PN junction that will allow the light to escape. Because if you didn't, then the energy is kept inside the diode, which would be your typical diode, and would either escape as heat or as energy back to do more electricity, if you like. I think if you were to look on websites like Wikipedia and see how diode lasers work, they would give you a nice example, an indication of how the electron band gaps work. I think it's best when you look and you have the diagrams to see it, because I have the diagrams that I have here is a little bit too involved. I hope that answered the question. Another question?
Yes, sir. Thank you so much for the answer. Yes, so the next question I'm going to be asking is the same person actually asked about masers. You talked about masers being the
Yes,
first type of lasers that we
yes.
produced. Can you explain a little bit more about masers?
So the maser is typically that like the cavity I showed you. And what it was, instead of it being regular, ordinary visible light or infrared and so on, it's just further down the spectrum. And so it was microwaves. So microwaves was the first thing they used. It's amazing how materials work, which is something to. So my first point to answer the question is physics is not common sense. Okay, this is why to produce any real work in physics, you need to experiment, you need to measure, you need to actually do something to prove what physics is. It's not logical. Physics is not logical. That however much science appears to be logical, it's not. And so what it is that you're looking and peering into nature and determining what the rules are within nature. Yeah. And then having determined that, you can then go on to come up with models to do stuff and all the rest of it. And it's the same thing with like, for example, the production of light. It was an idea, but then they had to experiment. And in that case, they use microwaves, because microwaves are easier to produce in the materials they had. And so if what's a good way of saying it? So I'm always enamored by, if you hold up a lens, and the electromagnetic spectrum goes along, where it's small wavelengths, which are very powerful, up to long wavelengths that have hardly any energy in comparison. You would think that materials is built, and the way we see through glass is that the small wavelengths will go through the glass and the long wavelengths wouldn't. And that would be your common sense way of thinking about it. But it doesn't actually work that way. So, for example, one of the questions that I would ask some of the students in the science room is, if we had identical twins, they're both the same in everything, as far as we can tell, and one sat inside the house and was looking through a beautiful brand new glass at a garden, and one sat outside on the veranda looking at the same garden, the question is, do they see the same image? That is, do they see all the same colors? And most people would say yes, because when you look through the glass, you can see the colors. But the truth is, they don't. The one who is sitting behind the glass has lost some colors, and the one outside is getting all the colors. And that's the most amazing thing about material. So if one is to look at the spectrum of any glass, you'll see that it goes up, and it will allow through these whole wavelengths, and then it will fall down. And even in some cases, it might only lose 5% of some of the energy up there, but your eyes is going to get the 100%. And that's typically what happens with most materials. So there's materials that are, when we look at it, it looks as if no light will go through it, okay? And so for us, it's opaque, and no light will pass through it. So we think, this will never let anything through. But that material may be completely transparent to microwave, okay? Or to infrared. And so that's the most clever beauty of it. So in the first instance, when they made the laser, they used materials for microwave energy, which is a much lower energy than visible light. And their aim was to basically prove Einstein, what would you say, theory on how light behaves. So that, Einstein did a work where I think he got a Nobel Prize for that one. What it was is he shone light on a material of different wavelengths, and he had a means of seeing at what point he kicked an electron off. And so that particular electron that came off, they would determine, they call it the work function. And it was from that principle that they went on to start looking at what things can be done. But it was Einstein's work in the original beginning that triggered the idea that they could do something like this, and to discuss the idea of having light that was in phase with each other. And so it's a whole history behind that. But if one looks at a maser cell is exactly the same as a regular light cell, a laser cell. So its production is very similar. Any other questions? Keep them coming.
Thank you so much, Dr. Paul. Yes, we have other questions, but they are basically related to the next session, the next two sessions.
You want us to move on, yeah?
Yes,
okay,
please.
Let me get the other one up.
So thank you very much to all the participants for your attention. We saw your questions, how you were following. Thank you very much. Don't get tired, stay seated. We still have a lot to learn today as Dr. Paul will be taking us on the next session, which is titled How Lasers Interact with the Body. So for the next 30 minutes, we'll be listening to a session. Just as usual, as we've said before, leave your questions in the chat box and we're going to take note of everything. Over to you, Dr. Paul, when you're ready.
Okay,
Thank you.
thank you. Okay, hang on, I've opened up the wrong thing again. That's a PDF. So we want laser interactions, yeah?
Yes, please.
Okay, brilliant. I have to share again, is that correct?
Yes, that's correct, please.
That's it. And then share entire screen. Right, can you see it?
Yes, we can see your screen.
Oh, great. Let me go back. Okay, so we're just going to have a look at some of the hazards and interactions, okay, of lasers. Right. Good. So what the outline is photobiology, the laser tissue interactions, eye hazards, and what to do in an emergency, and skin hazards. These are the things that we're involved with as medical physicists, okay? So with respect to photobiology, the nature and severity of the injury depends on how the laser radiation interacts with the tissue, okay? So, we have absorption and scattering properties of tissue, okay? The location and level of absorption in the tissue, especially with ocular tissue, which is your eye, right, is highly dependent on the wavelength because different tissue will absorb different wavelengths, okay? And then, of course, your absorption depth, how deep your wavelength is going to penetrate into tissue. And so that is what generally governs your photobiology, okay? So here's an example. So if you look, for example, with melanin, this is a response. So down here is our wavelengths. This is in micrometers. So this is typically your light range here. And here is the absorption, how much absorption is taking place. And so you can see what I meant. So when you have different material, they will have a spectrum of whether they let light through or not. I like to give an analogy again with this one, which is like there's a whole bunch of students coming out of class and they're going to go to parties in the evening. And there is 3 discos available, and each disco has different music, One will be, for example, heavy metal, one will be reggae, and one will be general pop. And what you'll find is that there's some who will go to the heavy metal club and they will immediately not enter because they just can't stand heavy metal and they go away. And this is your reflection. And so they just don't go in. And then you get the fans who love heavy metal, they go into it and they stay inside of it. So they're completely absorbed. And then you get the people who don't mind metal so much because they really like pop. And so they will walk in through the entrance door of your heavy metal club and they will walk through, they'll have a little dance and then they'll leave at the other side and go on to get to their normal club. And that's transmission. And that's typically what happens. And I always see it as a means of vibrations because everything in nature is about vibrations. And it's interesting. So just to give you an example, I think it's on YouTube. There is a professor from MIT who does a talk about why photons do not go through metals. And what he'll tell you is because of the crystal arrangement of the material. Now, when the photon impacts the surface, the vibrational state is up and down and not longitudinal, and therefore it is reflected. And when it's longitudinal, it will continue through the material. And interestingly, a lot of people don't understand that photons are basically pieces of energy, and it's basically how the universe transmits energy in many ways. is basically the greatest carrier of energy, are photons. And when a photon enters a material, whether it's glass, water, whatever, it becomes what we call a phonon, which is basically a sound wave. So it goes from being what we'd call typically a light wave and becomes a sound wave, because it's basically a very high intense acoustic shock that travels through the material. And so you can see that it's a vibration. And so if that material cannot vibrate at that rate, it will not have it. It will just not have it. And if it loves to vibrate at that rate, it will just absorb it. It will just become a part of the background. And there is the part where it can allow it through, but it won't absorb it, and it will just continue on its way. And that's basically how most tissue will interact with the different wavelengths, as you can see. So, here's just rough examples of your protein, your visible, your hemoglobin, which is your basically in your blood, your melanin, which is formations within your skin. Look at water. Water has a whole host of different absorption and transmissions, yeah? And all these things are relevant when we're going to create a laser, because when we look at the tissue that we're going to target, we want to know if it's going to absorb it, because most times when we're using lasers, we want it to be absorbed, yeah? And to take in that particular energy to do the work that we want, So, for example, looking here it's not a really good picture, but what we have is a green thing passing through one balloon and into another. So it can pop the balloon inside the other balloon. And that's amazing that the light can pass through without damaging that balloon. But with this balloon that absorbs it, it will damage it. And that's just a typical example, And so it's a 5 nanometer wavelength which passes through the outer balloon, but is strongly absorbed by the inner red balloon, which explodes. We need to do another one of this and have it much more clear. Probably do a video, which would probably be a good thing. And so that's how photobiology kind of works. So if we're going to go and treat tissue below the skin, we want wavelengths that are going to go through the upper part of your dermis without interacting with it too much, because we don't want to burn a hole through. And then we want to get into those lower tissues where we can do the job that we need to do, So there's a lot of skin complaints that get dealt with by lasers. For example, there's psoriasis, there's red port wine, and so on. And these things are things that will live on your skin. Lots of skin conditions lives on your skin, and your body is like happy to live with it because it doesn't really know there's a problem. But we use the lasers and damage the skin. And when we damage the skin, the body then says, oh, I am damaged. I need to sort this out. And what it then does is it comes along and it repairs it. So it's actually not the laser doing the repair, it's your body. But what we need to do is to tell your body it needs to repair itself. And that's typically the whole idea behind photobiology and the things that we do. We also can use lasers to trigger drugs. So you might have a drug that goes in your system. It will go to various areas where light can get through, and it's then triggered by using a laser. We can use a laser then to trigger it back. So we can use that in things like cancer treatments. We know what cancer cells love to consume, which is sugar. They love sugar. And so what we will do is we'll target with different molecules, which will be poisonous to the cell, but they won't interact with any cell till they get to the area. So we'll wait until the cancer cell eats up this very special sugar that we gave it, and then we will turn on the light. And then once it's in the area, we turn on the light, and the drug becomes activated and kill all the surrounding cells, which hopefully and technically will be the cancer cells. So that's another example of using the whole idea of absorption for particular cells and so on. So with our tissue interactions, once we absorb the optical radiation, the energy can be dissipated in two ways: thermal energy, which is heat, or a chemical reaction, so ionization or bond breaking. Okay, so basically we're doing a bit of destruction. So three types of interactions can be distinguished. We have photothermal, photochemical, and thermomechanical. And the interactions also depend on the wavelength, exposure duration, and the amount of tissue, or the tissue which is exposed, the skin or the eye. There's also other factors, for example, because your scattering comes into play. And so we might need to either increase the beam, the width of the beam, or the power in the beam, and so on. But these are typically your main interactions that occurs when it comes to tissue. And you can see here, we have the thermomechanical, which is up here. This is a power density scale. Here's your regular thermal, and down here's your photochemical. Okay, and these are your exposure times. So your photothermal effect, most common effect, right? So it's leading to an increase of temperature of the tissue, right? Injury occurs instantly. So you can see the temperatures involved here, tissue hypothermia, edema, your protein denaturing, your tissue necrosis, water and tissue boils, so you get tissue hydration, and of course, greater than that leads to carbonization and melting. So it depends on the effect that we want to have, okay? So while we're talking about injury, we have to remember that we're doing this injury on purpose. We're doing it because we want to do this, because we might be wanting to destroy particular tissue, okay? And I'll take a little time here to explain something. We often ask the staff and the people involved with treatments of patients, what do they think patients are coming into the hospital for? And then I will ask you here, if you thought about it, why do you go to a hospital? And if you were to ask a patient, what is it you expect when you go to a hospital? And their typical answers will be, I'm going there to be cured. I'm going there to be healed, and so on. And I'm going there to be treated nicely and to come out feeling good and working properly. And I always find that interesting, the view of what hospitals are. But in actual fact, when you think about a hospital and what we do, and this is something that you may not have considered, when you go into a hospital, these are the things that will get done to you. Let's give you examples of what hospitals do. You have surgeons. And if ever one watched a film that would have, for example, a serial killer running amok, and they would show him with his tools, the tools that they will typically show you a serial killer will have are the tools of an orthopedic surgeon. So he has some of the most gruesome looking tools. They're saws, they're hammers, they're all manner of stuff, because he's going to work on your bone, and he will need tools like that. And then the other thing is, when you come in, they'll say, what's going to happen? So you'll have the surgeon who's going to cut you. He's going to open you up. He's going to explore around inside your body, and then he's going to sew you up. And then another thing they'll do to you is that they will poison you. And how the poison works is that every medicine that is dispensed is a poison. And the reason why it's a poison is that it's going to go in and it's going to do a job. It's either going to destroy something that is causing problem in your body, or it's going to change the way your body works. And so in many ways, that's regarded as a poison. And so you're going to be poisoned, okay? And then what else will they do to you? I mean, if you even think of physiotherapy, the way they manipulate you and bend you and twist you up, it's really painful during procedures like that. But at the end of the day, it's all for your own good. So in actual fact, a hospital doesn't really cure you. What it does is that it does some form of injury to you. And then they will say to you when you're being discharged, we'll see you in 6 weeks. And they send you home. And so that 6-week period is a typical average time that your body will repair itself. And that's the whole point, is that with respect to all the treatments that we can do for you, it's all about getting your body to heal itself. Whether sometimes we remove things from your body because they don't belong. But again, at the end of the day, your body is going to have to heal itself. And so that 6 weeks period is typical healing time, unless, of course, it's like a broken bone, which will probably take a bit longer and so on. And so looking at the effects that lasers are doing, you can see that's what we're doing. We're going to boil tissue because we want to destroy it. We want to get rid of it, yeah, because it's causing a problem in your body. And so these are the things that we look at when we're using a laser. That's what lasers are. It's a tool for doing some kind of destruction, yeah. And then there's a photochemical. So it competes with the photothermal. So at particular irradiance, right, it's not high enough to do the thermal damage, but it's certainly going to cause a change. So UV energies are enough to cause ionization and create free radicals. You can have cumulative effect where short exposure of high irradiance and long exposure of low irradiance lead to the same damage. And injury and damage occurs after a period of time, several hours. So the damages observed will be skin burns, skin cancer, cataracts coming from being like, for example, being in the sun too much. It can cause skin cancer and so on. So if one was going to have laser treatment, the number one thing they will tell you is, they will ask you is, have you been on holiday recently? Because if you've been on holiday, they won't treat you. They will tell you to come back in a couple of months, because the sun does damage to the skin, believe it or not. And we may not notice it, but it has done it. If you then go on to add laser damage to it, you can trigger skin burns, cancers, and cataracts in a horrible way. So that's why we don't treat patients who've been exposed, and typically because of these effects. And of course, you're thermomechanical, and the term here is your mechanical. So you heat it up very rapidly and locally. There's a thermal expansion, okay, and it induces mechanical shock waves, okay? And these propagates in the tissue, causing more damage to the surrounding tissue. And so we can do ablation. It leads to ablation where you can take off layers. So you can get ultrasonic pulses 10 to the minus 12 picoseconds, as they have high peak irradiance and electric field strength and can lead to optical breakdown of the material. And again, so we're taking advantage of the physical effects of what laser light can do, and depending on the wavelengths as well, to create the kind of damage that we want for your body, in order to produce the effect that we want to produce, to start the healing process, and to get rid of whatever it is that is causing a problem. So particular hazards, okay? So here's your eye hazard. This is your typical eye, the pupil going in, and then here's the back of your eye, okay? And again, it depends on the wavelength. And here, down here, you can see the effects of those wavelengths. So you have your retinal hazard region, which is here. So that's the entire visible range, stretching into the near infrared. And that's why I was saying earlier, it's from 400 nanometers to 1400s. So these lasers, just imagine you're using these lasers. You can't see them, so you don't know that laser is on. But that's going to the back of your eye, and it can create problems for you. And that is your, at the back of your eye, where if you get a spot, like a burn spot, and we've had accidents in the past, in the early days of lasers, where it's burnt the back of the eye and it just can't be repaired. Somebody got burnt because they didn't wear their eyewear. So eyewear is very important. So that's part of my job as a laser protection advisor, is I look at what wavelength it is and the power concern. And then we use tables that are available in British standards and other places. There is international standards as well, the ISO standards, and they give the tables. And we do the calculations as to what strength of protection the eye should have. And really, it's much more difficult to protect your skin. It's just that we just say, don't go burning your skin, but at least your skin can heal. But with your eye, once you lose the vision, that's it. So we're very particular about safety with respect to staff who are going to work in a laser environment. And on this side here, where it's a UV, the main hazards, as well as your far infrared, is going to be at the front of the eye. So this sort of stuff will create cataracts. So this is something that is notable again. People who live at high elevations are more exposed to UV because there's less atmosphere, less thickness of atmosphere, okay, on the planet. So what you will generally get is that people who live at those heights will be more prone to having cataracts, mainly because of the UV. And so this you can see is expressed. But now that we've reached the point now where we can literally take lenses out and put new lenses back in. So part of the procedure in your eye is that they bore a 1 millimeter hole in the surface of the eye, and they go in and pull your natural lens out, which has become cloudy, and stick a plastic one in, which is depending on the agreement you had regarding what kind of vision you want, whether it's near, mid, or far. And they can stick it, and that can be done really quickly now. So medicine really has moved on. It's incredible. So that is the eye hazards coming, and this is a range. And hopefully you'll have the PDF so you can always refer back to this. So with the UVC, so it's absorbed by the surface, which is what we were saying, right? And high-powered lasers can cause ablation of the cornea. Example, the excimer laser. That's 308 nanometers. Right? And so if the peak power is not high enough to cause ablation, it can cause inflammation, which will develop after several hours. And so the one place that we use eximers a lot is in cardiology. So, and it's fiber. We enter the patient in their groin area, go up the vein, up towards the heart, and then there may be things that is causing blockages in the heart. We can use that laser to just burn in an ablative way all the stuff that is causing a blockage. And that's really brilliant because those particles are not big enough to go on to go cause things like strokes. You know, strokes are normally caused because something has accumulated and it will go somewhere and block a vessel somewhere in the brain. And then there is a lack of blood flow, which then causes a reduction in oxygen really quickly and leads to the stroke. So ablative lasers are very good like that because it's just taking away that issue, and then the body will naturally just gets rid of it. So if the peak power is not high enough to cause ablation, then it will cause inflammation, which will develop after several hours. And so typically that's what the effect of UV is. Then UVB, which is absorbed by the cornea and the lens. So for accidental laser exposure, the exposure level will be exceeding the threshold and can cause permanent damage to the lens. In which case, what you're looking at is new lens, which I just described, that we can replace the lens now. So that's not too bad. Note with the UVC, the 100 to 280 nanometers, this is the UV that you'll use to do disinfection, like you will clean surfaces, because this thing will kill bacteria. At that wavelength, you're killing bacteria and various other little things that are creeping around on your work surfaces and so on. But you have to wear eyewear with this, otherwise it will cause the blindness. And not to say that the rest don't, but this is particularly nasty. UVC is particularly nasty. And so and then later on, I think when you do your ultrasound, and I think there might be a UV thing course, they will go into these in more detail. And so, and then you have your UVA. It's absorbed by the lens again. Photon energy is not high enough to cause photochemical damage, but it can induce thermal damage. So basically all your surface effects are here and not at the back of your eye. So for visible and near infrared, C is the most dangerous part of the spectrum for your eye injury, because once it gets to the back of your eye and it does damage, well, that's it. There's no repairing that. And so this is the wavelengths that will be transmitted through this material that gets to the back of your eye. Yeah, and so it goes back to what we were talking about before, how different material can absorb different wavelengths and the way they allow them to be either transmitted or reflected and so on. And so for our eye, this is the wavelengths that we have to be very careful about, especially with your lasers. So you know if you're going to be in a room or anybody's going to be in a room, they should be wearing the relevant eyewear to protect their eye. Okay, and so that's where we get all worried. And so it's a 1 milliwatt per centimeter squared entering the eye would be effectively increased to 100 watts per centimeter square. And the reason for that is your eye is a focusing unit. You know, it's a lens and it's going to focus things to a point. And that's how you're able to see wonderful images, because light that is being reflected from everything goes in all manner of direction and your eye is capturing it. And another good example of this is when you're using telescopes to look at the stars. The larger the mirror, the more light that you will capture from that single point of light, that star that is in a distance. And so you get a better image. And so this is what it is. Your lens is collecting the light, and then it's going to focus it to a point where it becomes something that your brain can make sense of, if you like. Yeah. And now your mid and far infrared. This again these are surface effects. These wavelengths don't generally go deep, right? It's absorbed by the cornea here, and this one is the aqueous humor, which is your transmission liquidy looking thing in your eye. So, and it's caused mainly thermal damage, heating of tears and tissue, right? Flash burns, corneal burns, infrared induced cataracts. So pain triggers the aversion response, which may help to limit the tissue damage because it's happening at the front of the eye. But generally, you don't get pains at the back of the eye. You know, it's not really something that I've heard a lot of people experience. Some people do because there's too much light. It's highly intense, and basically your brain is saying, "Oh, that's too much." But these are things that we must keep in mind. So again, this is something that we would protect against. It doesn't matter. I have a rule. In fact, what we'll come on, I think we'll come on to it in the next one, but there is this thing called the NOHD, which is the nominal ocular hazard distance. Basically, what it means is if I have a laser and I'm going to point it at you, how far away from the laser have you got to be safe? That the beam will spread enough that when it enters into your eye, it's not a problem. Well, that's a pretty long way. And in some cases, some of the lasers that we have, it's only 20 centimeters. Okay, it's not even a foot long. And so what I do, I have a rule. I don't care. As a laser protection advisor, when we're designing theaters and the rules that I put in place, the local rules, I will tell them, I am sorry, anybody in this room have to wear glasses, because once you close the doors to do your laser work, I consider it a dangerous room, and I want you wearing your glasses. I don't care how far or how near that beam is. I want you with your glasses on, because I know what it's like when you get hit with a laser. Even if you're far away and the light goes off, it can be so intense and bright that you may temporarily be blinded. If you're holding something which is dangerous in your hand, you could cause an accident or have self-injury. So it's my rule to make sure everybody's wearing glasses. And so here's some typical examples. Here, look, you can see severe cataract in this eye here in the bottom left, okay? Right? And you can see all of the redness. Look, that's photokeratitis. I can never say these words, right? Which is comes from UV exposure. And then look, here's a boy was playing with a green laser, bought off the internet, right? And you can see that's a 532 nanometer, obviously, and that's it's look, partial vision loss. And this is how it heals after a little while. Doesn't look much better, does it? There is going to be a dark spot in his vision. Okay, and that's typically what it is. That's another thing I like to point out when I'm talking. When you're on holiday, there's always these little laser trinkets on sale in the market. They're typically keychains, and it has a nice little button where you can press it and you get these beautiful little red lights. I don't like them. The reason why those things have appeared on the market, stalled, and they're readily available, for the public, is because they've failed their classification. And generally in a fracture, when they've failed to be within the range that they were aiming for, it means because they failed, they put them out the back door. And so they're sold as a bundled thing in the back door. And all the warnings on them, we have tested them and we found that they're wrong. So they may say, oh, this is class 1. No, it ain't. It's not a class 1. Or it's a class 3R. No, it's not. It's a little bit too powerful to be the class 3R. And so my advice to people always is, when you get those things from the markets, you don't purchase them. If you do purchase them, the one thing you do not allow is a child to play with it. Because children have the habit that if they have anything that emits light, the one thing they're going to do is to shine it in each other's eyes. And it's a given that they're going to do that. And so that can cause injury. And so this is one of the advice I give. We do not play with stuff like that. And say, here's another example of eye injury. So a 21-year-old looked into the exit aperture of an infrared YAG. Now that's just like pointing a gun at your head and pulling the trigger to see if it has a bullet in it. And this is why I hate. So one of the things in my talk always when I'm doing the safety talks is you do not look in the aperture, all right? Or you do not look down the handpiece to see if you can see anything, because it might be the last time that eye sees anything. And so it's quite important not to do that, and because you can see examples of the injury. This is what it is. This is the 4 days after the accident, and this is 1 month after the accident. And so basically, if you ever come across an eye injury, the first person you take them to is an ophthalmologist. Eye doctors are really clued up on when it comes to lasers with the eye, and they're the only people that you should really go to first. I mean, of course, you go to your A&E department, but really you want to be seen by an eye doctor, because they're going to be able to examine the damage and make the proper assessment of what is wrong. Right? Dazzle. So this is the other thing. Now, your laser may not be dangerous for your eye in terms of causing a burn or anything like that, but the other effect that it can do is a dazzle. And so there is new laws here, for example, in the UK, where if you point a laser at a helicopter or an aircraft, you're going to prison. And the reason is dazzle is an amazing thing. Dazzle can cause after effect images in your eye. It's similar to like when you're driving at night, it's probably raining, and the headlights from these new cars, which use LED headlamps, are very dazzling. And so it reduces your vision. And if you were to look up suddenly and that guy didn't turn down his beam and had it on high beam, you would certainly be affected by it. There's a temporary blindness. And there is the after effect where your eye is recovering from that sudden piercing light entering in your eye. And so this is another effect from your eye injury from this kind of light. And so we guard against this by explaining to the users inside the theater that even though the laser may not be dangerous, there will certainly be the dazzle effect. And if you're working on a patient and you were to be flashed, then the last thing we'd want you doing is holding some dangerous implement in your hand and not being able to see what's happening. And so that's certainly an effect that we are aware of. You can see why I insist that once people are in the room, everybody's wearing their PPE, right, which is your personal protection, because you cannot afford to have accidents, okay? Not with lasers anyway. So skin injury is a little bit different. It's quite secondary to eye injury, okay, because they typically will heal, though in some cases it can leave scarring, and that's something that we have to pay attention to. So when laser doctors are going to do skin treatments, for example, they may not start your treatment straight away. What they'll do is they'll do a test patch, and they'll tell you to come back again in your usual 6 weeks period. And the reason is they need to see how your skin heals. And so there is 5 tones of skin. Okay, it's a range going from dark to light. And it's amazing that you can get 2 people that have the same lightness, and yet their body will react to that same energy and wavelength completely different. So you cannot say every human being that comes along that looks like the other human being is going to be treated the same way. No, it just doesn't work that way, because we have subtle differences in us. Each of us, we're kind of unique, all of us. And so that's why they do test spots. They do a test spot on your skin to see how it's going to heal, see if there's going to be any scarring. You know, nobody knows how each of us is made up 100%. And so this is why they'll do it. But you can see here, these are your different depths that your wavelength will go. So here, this is your surface. You can see your excitement doesn't go in. This is your UV. It doesn't go deep, okay? There's typically your CO2 will just get a little bit deeper here, but it doesn't go all the way in. So this can ablate this layer quite comfortably, whereas that will only take off a super fine layer, probably just your first surface skin, okay? This is your erbium YAG. So that's 2,940 nanometers. That goes a little bit down in here. So again, the erbium, the CO2, all of these lasers here are fondly used by dermatologists, because the dermatologist is always interested in your skin, and he's looking to treat what might be wrong. And you can see some of them just goes and it stays in the epidermis. This is the PDL. This is a dye laser. Okay. This is a KTP. So this is a 532 nanometer laser. And this is these. I like these lasers because they generally have 2 wavelengths. They have a 1064 and a 532. And what it is it's a crystal with another crystal behind it. So when it produces, they produce a laser light of 1064, and 2 1064 photons will go into the other crystal and mix and join their energy by pushing the electrons up higher and produce a 532 nanometer photon, which is quite clever, I think. You know, I wonder whoever came up with that, or they may have discovered it by accident. And then, of course, the ruby goes quite low down in your skin. See, you can see, well, deep, but we no longer use rubies as such. I think rubies are taken out now because of the type of treatments. We have much better lasers that are available. For your example, your Alexandrite, your 755, your diode going deep in, and your Nd:YAG going deeper, you see? And so all of these are used. And of course, the effect on the skin is all dependent on these factors: your wavelength, your power, your spot size, exposure duration, your blood circulation, heat conduction of exposed skin. So as said, the skin injury is secondary to your eye, and it will heal, okay? But what we don't want is scarring, okay? So here's your injuries. You have burn, thermal injury, and for example, sunburn, photochemically induced injury, okay? So UV can lead to skin reddening, also called erythema, high radiance, short exposure, and low irradiance. Long exposure produces the same effect. And you're visible. High radiance or high radiance exposure cause thermal damage and may affect skin pigmentation. That's another thing that can happen with your skin. It might affect your pigment. And then there's infrared. Near infrared can penetrate deep into tissue, causing serious injury. So far infrared laser, example, your CO2 absorbing the surface layer of the skin, but can cause carbonization. And we would use a CO2 to basically cut through the skin, because when you bring it down to a point, it becomes industrial. That's what it becomes, in my opinion. And it's able to just cut straight in. So very good for cutting things like keloids off the back of your, your head and on your neck and areas like that. And as well, remember what I was saying, it cauterizes as it goes, so it seals the skin. So you can see some burns here. This is from hair removal, and you can see where the treatment protocol was not followed, right? And that's the scarring that is left behind. Okay, so obviously that's a problem because a lot of beauty clinics are offering hair removal, and oftentimes they'll get these kind of problems and then wind up coming back to us in the hospital. And so what we would have suggested they do is to do a test spot, because if they'd done a test spot, they would have known this person is prone to scarring for these wavelengths, and really should just leave well alone and look for a different method. And you can see here again, this was hair removal used on a tan leg. So no, do not go into the sun and then get treatment, because you can see here there's a loss of pigment in the skin. Okay, and so laser beam can cut through your finger of the staff. Look, he was doing alignment. You can see that. So you don't mess around with lasers. They can cause serious injury. Okay, now, so these are examples of skin injuries. You know, this will not heal readily. I'm not quite sure at what stage this injury is being shown, but that will not heal readily. However, I will say, for example, we have an incorporated children's hospital, the Evelina Hospital, and I remember once a child was going to get treated for port wine stains on its skin, and it was really horrible. It was all over the body. It was this red tissue where the body has just been living with it, and so it was going to go in and get full treatment. And I don't think the plastic surgeon had completely explained to the parents what the child was going to look like when it came out. So I did say to them, yeah, I say, your child is going to come out looking as if it's been in the worst fight of its life. It's going to be totally black and blue over. But I guarantee you that in 6 weeks, you'll be back to ask the doctor to do more. And so when the child came out, I could see the shock on their faces. But they were cushioned because I had explained it. And then they went, and I saw them again in 6 weeks, because that particular laser was a kind of tricky laser. So I was always in attendance with it to make sure. And I saw them come back and they said, you're right. We do. We are back for more. And I was just like, yeah, I told you. So it's amazing. So immediately after treatment, the skin will look really bruised and terrible. Like I said to you, when you come to the hospital, that's what we're going to do to you. And so, but once the body is healed, it gets rid of whatever was causing the problem, and the skin returns to normal, which is really good. Yeah. So, in summary, you have all these various eye injuries caused by these different wavelengths, and you can see them. You know, so for us, the visible and the near infrared are very damaging for us, and so we want to avoid these basically. And basically, we do that by wearing the correct PPE. With the rest, we know it's going to be surface, and if you're near a very good eye hospital, they can probably give you a new lens, which will correct that. But best avoided, in my opinion, yeah, rather than to suffer the injury. But remember, between these wavelengths, you don't mess around, because that's a one-time hit, and a one-time hit is enough to lose your eye. Okay, and so for emergency procedures, which is what we always say, you must get a full ophthalmic examination. I think I spelled that wrong. Must be undertaken as soon as possible, and in any case within 24 hours. What a good thing to do is to fill in what happened, explain it, where it happened. Other settings, you must record the energy, the pulse duration, the wavelength, and so on. Because the more information your ophthalmic surgeon has, the more he's going to be able to help you. And of course, typically if there's a injury, you have to secure the equipment as well. You contact all your laser safety person, headed up with clinical laser specialists. And of course, you got your exam, all right? And typically, if you follow the path of lasers within medical physics, you'll probably wind up being a laser safety officer or a laser protection advisor or laser protection supervisor, one of those things, then you really have to be versed with what your emergency procedures are and how best to respond to incidents, because that is you. If by responding, you're going to certainly help. But remember, your help is going to be more from a scientific perspective. And it's good to take the notes down because you need to know what happened so that in any local rules that you produce for the department on another time, it's going to cover the possibility in your risk assessment of that happening. So you want to iron it out and work towards having a risk-free environment, if you like. It will never be completely risk-free because they are using a dangerous instrument, but you're going to reduce the risk as much as you can. Okay, and that's the end of that one. Any questions?
So much.
Are we all asleep now?
No, you're here, definitely. Thank you so much, Dr. Paul, for that insightful session. It was really a lot to learn. I mean, from how the lasers interact with various tissues in our body to understanding that those little key rings that we all used to buy like as a toy,
That's
it's
right.
actually not very
Not
good for
safe.
health.
Yes.
Thank you so much. Thank you so much. And I mean, understanding as physicists the different effects of lasers is also something to pay attention to. So we
Yes.
understand that like there are different effects, the photochemical, the photothermal, and the thermochemical effects. Thank you so much. There are a few questions, but just before we go to the questions, we are going to do a short poll just to get everybody involved once again. So I'm going to be launching the poll and it's just going to be for a few seconds. So do well to respond to the poll. Let's see how far you have learned today. And yes, it's going to be an attendance for the conference. So please ensure you participate in the poll as this is going to determine your attendance for day one. Thank you very much. So that is it launched. Everybody, let's try to participate. Let's try to participate. Okay. Let's keep it going. We have 19% participated now. Let's keep it going. Keep it going.
Maybe you should share the QR code so that no one is left behind.
Yes. Can everyone see my screen, please?
Okay, we can see now. Yeah.
So I've just shared the QR code. If you're not able to see the questions, just scan the QR code and you'll be able to do that.
Okay, that makes sense. Okay. Let me scan.
I can't see the QR. Where would you have the QR code? I can see that you're saying day one laser poll.
Yeah, that's the QR code.
Okay, you're going to share, yeah.
Yeah, so if you just scan the QR code.
Okay, I think that's fine because of time.
All right, so I'm ending the poll right now. Thank you very much, everybody. Okay, thank you for participating, everybody. Thank you so much. I hope you had a good time doing that. All right, so just a few questions and we'll quickly go into the last session so we can then answer all the other questions together. You've basically talked about this, but I'm just going to ask two questions that are similar. This was someone talking about the football fans shining lasers on the footballers. And then when you go to parties that use laser lights, is someone speaking?
Sorry. They're breaking up.
I can hear someone speaking. Can you hear me now?
Go ahead, please.
Okay, thank you. So the first question is about football fans shining lasers on the footballers. Does that have negative effects for the footballers? And also when you go to parties and there are after parties that they use laser lights.
There's somebody talking.
Yeah, I can hear someone talking.
Don't worry, I need to mute him. Is the SG. His network is bad. Just go ahead.
Okay, apologies for that.
So, yes. So, yes, this has been an issue. So, it's nightclubs. Nightclubs are problematic because you get your beautiful green and red and blue lasers shining up and down inside of the club. What we look at is the beam spread. So they're generally lines or they're conical, shapes going out, and is with respect to the distance. So if your lasers are in the ceiling and they're shining down on your audience, and your audience are at a certain maximum height, say, so you choose the highest person you think that can come into that club is probably going to be just under 7 feet, is going to be your highest person. Then that distance with respect to your cone, you can calculate out and work out if it's going to be dangerous at that point. So, not sure if I followed this in the next thought, but to explain, there are particular values that we hold precious in lasers, and that is the size of your pupil. So the average size of a pupil, we consider it to be 7 millimeters in regular ambient light. Okay, and that is the size of the pupil. So that's the size that's going to take it in. However, in a darkened room, your pupil will open. That means it's going to take in more light. So your susceptibility for the amount of energy going in is now greater. Okay? Even though the room is darker, but it becomes a bigger problem. So if a laser was to hit you when your pupil is nice and closed because you're in bright light, it's less damage than if your pupil is open in a dark space, because most of the light is going to go in. And so they now have laser protection advisors in the UK who are now geared just to look at those events. So they go along, they see how the event is going to work, they look at the energy with respect to those lasers for those events, and then they calculate out what the risks are. And if there's a risk that is going to exceed what we call the MPE, which is a maximum permissible exposure for your retina for that wavelength. And every wavelength has a different value. And so there's tables that shows the ranges for the different wavelengths. So they look at, if it's going to exceed that value for anybody there's a risk of that, then they can say to them, there's a risk. And if there's going to be a risk, they can literally tell them, no, you can't use it. And so the laws are working to change these things. With respect to handheld lasers at football fields, that's just illegal. That's just wrong. And it's down to the governing bodies of those matches to make sure that they isolate those individuals and get rid of them, because they're just there to cause problems. And I can see why they're going to do it. It's going to be the fan of one team trying to upset the footballers of the other team so that they will fail in seeing the ball when, like balls are being passed and so on, in order to give their team an advantage. But that is absolutely wrong. And while there may not be a specific law saying you've shone a laser light, you've got to look at the fact that they have done something which is wrong. So there's other methods in the law that they can use against those individuals, But certainly with the football governing body for the stadium for that particular day, they should be able to act and send the stewards in and kick them out of grounds, because that's unacceptable behavior, and definitely could cause injury. So you're putting somebody else at risk. So yes, shining any kind of lasers at events is an acute problem. Yeah. And, that's why I was saying to you earlier that if you, in this country now, if you shine any lasers at any aircraft, you're in serious problems. So one of the things that protesters do is they will shine green lasers at police helicopters who's monitoring the crowd. What they don't know is that these police helicopters have equipment in it that can isolate a laser to within 2 meters, even in a building, even if it's somebody's standing in a flat somewhere, in a group of apartments, and they shine a laser at these helicopters, they can isolate it to what point and to which apartment that laser beam came from, because the equipment is in there sensitive enough to work out direction and angles, heights, and everything else. And generally, what happens to them is that the police turns up at their door and they're really surprised, and they go in and say, "Where's your laser?" And they don't only take the laser, they take the individual as well, because he's going to court the next day. And so the rules governing lasers is getting tighter, certainly in the UK. I don't know about the rest of the market. I mean, I can go into the web right now and I can buy myself a 20 and 30 watt laser. And why would I want to do that? Not unless I'm going to be doing some kind of physics experiment. I have lasers that I use in experiment, but I use them in very controlled environments. And I certainly wouldn't want to go and buy something off eBay or Amazon or wherever, and then think that I'm going to use this in my experiment. It says 30 watts and I'm going to trust it. Yeah. And imagine as an individual who hasn't got the training or the equipment to measure those lasers, they're going to make mistakes. And they're probably not going to even have the correct eyewear for those lasers. And again, they're running risk against themselves. One of the biggest problems with lasers is reflection. So, if you have any shiny surfaces, mirrors or anything, you can't have those in theaters. You can't have them in the room that you're going to use lasers with. You're going to get rid of them, because once they bounce off that, they will come right back onto you and cause a burn. So yes, those issues are a risk. Any other question?
Thank you so much, Dr. Paul, for that answer. I hope we all understood that. So before I go to the other questions from the chat, Dr. Ibusa has a question, and I'll allow her to ask the question quickly.
Okay, thank you very much. And apologies to those who are asking questions. I just wanted us to connect it with what is going on back here. Dr. Paul, you're in the UK, you're a laser specialist, and you have all these laws. And what about in Nigeria and other African countries where we don't have this kind of specialists? What can we do in the interim as physicists? For example, you were talking about lasers being used in tattoo parlors, in beauty clinics, for hair removals. These are very common procedures that are done now by a lot of young people. So I'm just concerned that, these tattoo parlors, are there people who are checking the safety of these equipment, the QC, QA and all this? I'm just really concerned about safety of all these things. And the toys we're talking about that children play with, for example, we don't have laws. These things are in the market. I see them everywhere. And we don't have police like in the UK who is going to arrest these people because they don't even know about this thing. So what would you advise us as physicists? What can we do in the interim? While we are thinking, of course, long term to get people to go into this area of specialization, but what can we do now in the interim as Africans who do not have these policies and specialization?
So I know this is something that has to be worked on and developed. Yeah, I was talking with another fellow from Jamaica, and they're trying to get their act together as well. So there is a document, and you can make notes on this because globally you can get access to it. The organization in the UK is called the MHRA. And if you get onto their organization, it's a web page. You can just search on the web. They're the medicines people who look at equipment to check them and they record all the incidents and everything. It's called the MHRA. And if you get onto their website, they do a book, a PDF, which covers all things lasers. It's incredible. It's a great awareness, how to create the local rules, how to do the risk assessments, talks about all the necessary issues surrounding lasers and light, yeah? And I think that's a good document to start from, yeah? I will always recommend this document. I should have it here, let's see. If I sent it to you, Ayo, will everybody get it?
Sure.
Yes, please.
Yeah. Okay. So I'll send it to Ayo Abasa, and she can pass it on to all those who are on the list. Yeah, definitely. I think that's a great document, and it covers so much, and it's a good start, even for those who have the clinics and stuff. Now, generally, when you have people with private clinics, what they do, there is certainly a supplier of the laser. And the supplier normally has a application specialist. That is a clinician or somebody who is very familiar with doing the procedures that they're going to use the laser for, that can train them. Okay? And sometimes the people selling you the laser, the salesmen themselves are the application specialists sometimes, not always, but you know. And so I think that is their first reference point, is to go back to the company selling them the item, unless they're buying it secondhand, which is where it becomes a gray area. But typically they can look up who will be an application specialist with respect to that laser for procedures in beauty clinics, you know? And at a minimum, they can go on the web and look at AI is wonderful now. You know, you can do fantastic searches on procedures using a particular laser, if you get what I'm saying. And that will come back with a lot of feedback. Not to say you should be trusted 100%, because AI doesn't get it right 100% of the times, but that is also a good starting point. And until an effective medical physics service is developed that can also offer its services to private organizations, you know, because they can rent your service, because we do that. We look after private clinics. So, you know, you might have heard of famous Harley Street clinics in England, in London. Well, we look after a few of them. So we will go along and ensure that their laser safety is correct. As a physicist, you're not responsible for dictating, and I always make this point, clinical procedures. You're not a doctor, okay? So you can advise on how the laser work, what is the technology behind the laser, what it may do to skin or eye, but you're certainly not there to tell them how to treat, because you have to remember, and I like to point this over, our doctors today, our modern doctors, are equivalent to our ancient shaman. Okay? He's our modern medicine man. And that means he has a power that you don't have. So if a doctor gets something wrong and something goes wrong with a patient and he's taken to court, he can say, I did my best for the patient, but it didn't work out. And he will walk. However, if you're the one advising and say, oh, this is what you should do, doctor, and you've gone and told them that, and something goes wrong with the patient, it's quite likely you're going to jail because you're not a doctor. And so you should never have given clinical advice, okay? Because that's not your remit. You're a scientist or an engineer. And so what you have to remember is your remit is confined to that. So you can explain the way the equipment work. You can explain the dangers behind it. You can say, well, this is likely to be the effects it will have, but you do not tell them this is what you should do. Am I clear on this? Did I get that across?
Yes,
Yes,
thank you.
sir.
Excellent.
Yeah.
Is there another question?
Thank you so much. So we have a lot of questions, but
That's
we want
fine.
to proceed to the next session.
Okay, I'll
We
get it
would
ready.
please love to ask Dr. Paul if you could please help us shorten the next session so we have enough time to like take the
I will do that. I
other
will do that.
questions, because we're
Fantastic. I'll
going
do
to
that.
finish by 12 as stated. Thank
Yes.
you so
Okay,
much. So
cool. We'll do
over
that.
to you
Yeah.
when you're ready, please.
Okay, we'll do that. We'll kick off now.
Thank you so much.
Can you see the slide?
Not yet.
Didn't share. I need to remember to share. Where's my share thing? There we go. Okay. And then bring it up. is it here? Right. Can you see?
Yes, we can see your screen now. Thank you.
Okay, brilliant. Okay, so we're going to have a quick look at clinical laser applications and laser safety. Okay, so we'll just kick off from here. Right. So here are some of the areas that lasers are used within the medical field. Right. So we got ophthalmology, dermatology, dentistry, urology and gynecology, surgery and oncology, cardiology. Yeah. It's not a complete list, but that's just some of the areas that the laser is a tool, like any other tool. So in ophthalmology, and they can deal with retinal disorders. So photocoagulation, organ lasers, treats diabetic retinopathy by sealing leaking retinal blood vessels. Trabeculoplasty, organ diode laser improves fluid drainage in glaucoma. Then you have this. It's just examples of the treatment: refractive surgery and pathology, LASIK, which is laser assisted in situ. Again, another word that I hate pronouncing, creates a corneal flap, then uses the excimer laser, which is your UV laser, yeah? And then small incision lenticule extraction, femtosecond lasers. This is something we're not looked at, which is a 10 to the minus 15 second laser, highly minimally invasive. This is a clever laser in that what it does, it's the doctor sets up a treatment plan, you sit in the chair, you look at a red dot, and then AI takes over. AI decides when you're looking at that red dot, and in the time when your pupil can move, because our pupils are never still, it's always constantly moving. But in the time that your pupil can move to the next position, it could have done 400 shots in your eyes. And that's because it's 10 to the minus 15 seconds each pulse. So that's so fast, it's unbelievable. So like in dermatology now, yeah, they target hemoglobin, right? Oxyhemoglobin, that's your vascular lesions, spider veins, birthmark. This is your port wine stains as well. Okay, rosacea, right? So it causes coagulation of blood vessels without scarring the skin surface. Typically, you will use a pulse dilator, that's a 595 nanometers, or Nd:YAG 1064, or KTP, which is at 532. So you can hear that. So that's two visibles and one very near infrared. Okay, that's typically what you want for these kind of things in dermatology. Also, you get pigmented lesions and tattoos. So they target here is the melanin, the natural, and exogenous tattoo ink. So age spots, liver spots, then you have all these specialist spots, amateur and professional tattoos. Ultra short pulses shatter the pigment particles for immune clearance. So it's your body that gets rid of the particles once they shatter them. And the pigment particles that they're destroying is dye pigments, because that's typically what you would have used, in your tattoos. Q-switch rubies, alexandrites, and Nd:YAG. Picosecond lasers are newer. So these are really fast pulse lasers. So you can see your Q-switch typically 4 nanoseconds and so on, along that length of time. Your Nd:YAG tends to be a bit like decades, they're tens of nanoseconds, but again, still equivalent, but they're really good, really fast. Remember, you're doing massive destruction, okay? That's why you're using your Q-switch in a very short period of time. Therefore, no heating of the skin, all right? You're doing explosive work and moving on, and that's it. And then generally what you do is you cool the skin. You'll probably have like a cooling spray that will cool the skin just before delivering the shot. And of course, you have melanin in hair follicles, so you do hair removal and rejuvenation. So you can fire, when you're firing down in the hair follicle, you're trying to destroy the center because it's hair removal, yeah? So these are typical lasers that you use, your alexandrite, your diode, and the Nd:YAG. So dentistry, hard tissue in the teeth. So you use an erbium YAG. The laser, it prepares cavities, so it's drill-less. So you're not going to be using drills. You're going to burn your way into the teeth using an erbium YAG, right? And it treats hypersensitive seals, tubules. And then for the soft tissue and gums, you'll use your diode, your CO2 for the various issues that you can have on crown tightening. So lasers finding their way into everything. So urology, kidney and ureteral stones, yeah. So there's a holmium YAG, it's a gold standard. We have about 3 different holmium YAGs where I work. And they're all fiber. And so you're basically going inside to do your work. Okay, then you have soft tissue, vaporization of prostate tissue. And that's because then it's a HOLEP, but again, there are holmiums. And the reason what you're doing here is that you're getting rid of tissue because you're reducing prostate tissue, which is an issue with older men. Typically, the prostate gland starts to enlarge and will block the urethra, so weeing becomes a problem. So you create holes so that urine can pass. That's just one example. So you're vaporizing the prostate tissue using your holmium YAG and thalmium. And the new one is the green light. And also it's used on cancerous tissue by destroying it. So gynecology. So that's another thing, genital warts. So it's in lower genital tract. All these are all different treatments. It's CO2 for ablation, because with warts, the problem with warts, doesn't matter what kind of wart is, we're not too quick to cut them, because generally you cut warts and they can become something else, typically something cancerous. So generally, if you're going to get rid of them, you want to ablate them off completely. So you can use like freezing. Freezing is one way where you can freeze it and destroy the tissue by freezing, or CO2. CO2 is just brilliant. You just constantly ablate it while just standing there and it's just gone. And you can leave a little depression where, just to ensure that, all the weird tissue is gone, right? And so you can treat all kind of stuff, just urinary incontinence and that kind of stuff, reproductive surgery, going inside, lysis of pelvic adhesions, and CO2, Nd:YAG, and KTP lasers. Now, the CO2 is a relatively long wavelength and is no good going down an optical fiber. So what they have now is hollow fibers which have a hollow metallic tube, which is bendy. And now we're able to bring CO2 down a fiber, so we can go inside a patient with a fiber and deliver CO2 work. So general surgery and oncology, that's basically ordinary surgery and cancer treatment. So the CO2 acts like a light scalpel, which is why I was explained before, is brilliant because it cauterizes at the same time. The diode and Nd:YAG for liver and lung resections, so it can go in. There may be stuff that you want to get rid of and cut out or open up pathways. You can do that. Tumor ablation. So you're basically just going to burn away the tumor, right? And you can put it directly inside of the tumor in liver, pancreas, and prostates, and thermally destroy them from within, So that's one way. You can also do that using nanoparticles of radioactive material. You stick them in, they have a certain given half-life, that is a time before they disappear totally as a radioactive item. And you can stick it within the tumor, put it right into the heart, and you destroy it from inside out. And then cardiovascular. So, it's peripheral and coronary angioplasty, treats complex arterial blockages, pacemaker lead extraction, vaporizes scar tissue binding leads to the heart or veins, and that's typically your excimer fiber laser. Again, we enter from the groin area and we work our way up, and we will use some fluoroscopy, X-ray, to see what we're doing in cases like that. And sometimes the patient will be given something that will highlight their veins so that we can have a better image, There's a word for it, I can't remember it right now. And then gynecology, of course, your lower genital tracts, genital walls. We've gone through this. We've done that. Okay, so general laser safety in the clinical environment, yeah? So you can get contraindications resulting from treatment. And that is, we've treated a patient and they've developed another problem. And so we need to be able to see what is it, what created that adverse effect. Okay, were they in the sun? Did they go on holiday just before getting treatment? That's one thing. Are they on particular drugs? we may not know about this. So it's good to find out all this you can about your patient before treatment. Even if you're running a beauty clinic, you should know about your patients. No laser treatment should be given to anybody who's been on holiday or have experienced a certain amount of sunshine. So if they're going to come and have laser treatment, one of the things to say is, can you wear long sleeve clothing if you're going to have treatment on your arms or wherever you're going to have that treatment, it must be covered for some period of time before that treatment takes place. Yeah. And so on, and what drugs they're on, and so on. Then the other thing, staff behavior. You need to develop a good working culture with your staff trained in laser safety. So we do that all the time. What we do is we do quick 1 hour courses. We can go in, we can literally say to them, we'll do it in your lunch hour. You can have your lunch while we're talking to you, and we go through the safety. And so nobody should be in a laser room without first having some form of laser safety training, even if it's just a basic one. They should not be in that room because they have to have an idea how to work safely around lasers. Because the last thing you need is somebody who's going to go in there and they're being flippant, and then they are the cause of the accident. Okay. The environment, you've got to pay particular attention to the environment and make sure that the area is, it's a good working area. You don't want to be tripping over wires or machines. You've got to have everything in the right place so that when you're going to do your work, it's free from clutter and everybody is able to move around. Because, in theaters, it gets really busy. You'd be surprised how busy it gets. And everybody's moving around like no man's business. And so you want it so that there's nothing in the way where you're bouncing against each other in order to get from point A to B. So, and equipment. Most of the incidents that occur with lasers is generally because they haven't been serviced and they're not in good working order, which is why we do quality assurance tests. We always go along, check that it's working within manufacturer's spec. We normally use a meter to do that. The meter we use typically have heads which are black bodies. That is, when you look at it, it's black. And the reason why we choose a very good black is black will absorb heat, but also gets rid of it really quickly. So if you're measuring a temperature with a black body, it absorbs it really quickly. The temperature sensors records it. You get your wattage or your joules, whatever it is. And that head is cooled and ready for the next shot, And so typically that's the kind of stuff we will use to measure the output of lasers. There are other hazards that you have to be mindful of. Electrical hazards. We tell people, you're not an expert. Do not open a laser. You can't fix it. Because it's highly likely if you go playing around in there, what will happen is that the doctors will be treating you for high voltage burns or you'll be dead. It's one of the two. So don't go opening up a laser. Then there's a mechanical manual handling. A lot of them are large and they're on wheels and heavily and they move around in odd ways. So we always say, be careful of that. Know your kit, know what to do. Chemical, you get your dye and vapor lasers. They're toxic and carcinogenic chemicals. If a dye laser leaks in your theater, you're certainly going to know about it. That smell is going to hit you like no man's business. So my thing is that if you walk into a laser room and you can smell it, the first thing you do, you open the windows, you come out, you close the door, you leave it be, yeah? And let it go. And then you call somebody who's responsible for it. Smoke and vapor, always problematic when you're dealing with skin treatments. If you've ever been in a dermatology room when they're doing CO2 work, you will think that you are at a barbecue and they're doing wild boar because that's what the smell is. And the room will be that smoky. So generally what you need in place is you need proper smoke evacuators with proper filters so that you use it at the site where you're working. And that sucks away all of the things coming up from that, because don't forget, there is bacteria and virus on everybody's skin. And when you're hitting somebody with a laser, that is going to create an explosion, and that's going to put that in the atmosphere. And people have no idea how fast explosive skin moves across a room. It's like half a second to move across a room of, say, 2 meters, really quickly. And then you'll be breathing it if you haven't got in the proper breathing apparatus, like your decent mask. And then, of course, there's fire and explosion. So no alcohol. You don't wipe down the patient's skin with alcohol before treating it. You use water. And that's something we have to keep reminding people. Then you have to have laser-proof tubing for anesthetic use. There's tubing that you put down to go into the lung to help the patient breathe when they're in general anesthetic. We've had laser fires from that. And so you have to have the laser-proof tubing when you're doing work like that with lasers, And your fire extinguisher. The modern rule now is to get all these foam and powders and stuff. Let me tell you, they all fail at 1,000 volts. And with your high voltage laser, it's not going to work. The only extinguisher that's going to work on your laser when it's on fire is a CO2 laser. And that's because it's a gas that starves that fire oxygen and puts it out. And so just remember that, okay? So that's your typical hazard. Now, when it comes to laser safety management and setting something up, these are the three areas that you'll cover. There's the administrative area, which is the risk assessment, the local rules, organization safety policies, contingency plans, and training. Then there is the personal protective eyewear. So you've got to get the proper eyewear for each laser, right? And everybody has to wear it in the room. And you have to have high quality and laser standard face mask because if there's smoke, right? And then, of course, you have your engineered controls, door locks, blinds for windows, laser warning signs, and safe laser key storage. You don't leave the key in the laser so that anybody can come in and turn it on. Okay, you put it in a safe space, and the person who's responsible for the laser is the one who will have to be asked in order to retrieve it. And so door locks are important. You don't want people walking in just as you're firing because they're not wearing their glasses, and they're going to certainly, even at a minimum, are going to be dazzled. Yeah. And for your windows, you want blinds because you don't want the laser light going through the window and out into the public. And this is, so you set your environment up to be safe as well. So at the heart of laser safety, I'm asking you to research further things. The MPE, which is the maximum permissible exposure. It's a maximum amount of light for each wavelength before it starts to cause damage. It's different for eyes and skin. Your nominal ocular hazard distance. It's the distance you can stand from the source of a laser, which has a beam that is gradually spreading out. The optical density. This is a value listed in laser eyewear to show it's safe for a particular wavelength and power. It's a logarithmic scale. Okay, so the American standard is you might see OD5, OD6. In Europe, you will not only see OD, you will see L, or you might see LB preceding the number. And the number always represents the number of zeros behind the one. So if you saw OD5, it means there's 5 zeros behind your one, which would mean 100,000. If there's 6 zeros, you know it's a million. And that's how many times it reduces the light from the laser going into your eye, okay? And then, of course, in terms of international determination of safety of laser, is called a class. So class 3B and 4 are the highest classifications of laser output powers, and these are typically the ones you will find in medical environments, including outside clinics. And so these are all dangerous. So typically, you need to be wearing the proper PPE on your eyes for those lasers. Okay, and I hope that was quick enough. Let me just close this.
Thank you so much, Dr. Paul. That was very quick and very, very insightful.
Yeah.
And it has really answered a lot of questions we had. I mean, people asking for what are the PPE for laser lights. The last few slides explained that. And someone also asked the question if wearing dark glasses would actually save from laser lights used in party. But from the last explanation, we can see that there are actually specifications for glasses used for protection against lasers. So
Yes,
that would answer the question to the person that asked if dark glasses will help. No, it's not going to help because there are specific glasses,
that's right.
specific glasses for laser protection.
Yeah.
Okay, thank you so much once again. So this goes to all participants. We will be putting a link in the group chat, in the chat box. Please kindly fill the Google form, and that's going to be as an alternative for people that were not able to fill the poll earlier. So yeah, we're just going to leave it there till the end of the meeting. So you're not having any network issues or anything. Please fill the And for people that were able to answer the poll too, please also do well to fill the Google form. Thank you. So I'm just going to go ahead to the next couple of questions we have.
Good.
So we have one question. It's probably related to the physics of lasers, but I'm just going
Okay.
to ask that. So someone says, if I assume that all lasers have different specification, should I also consider that the absorption coefficient depends on the laser that we are using?
Of course, 100%. So your laser absorption is totally dependent on the wavelength for a start, okay, and depending on the type of tissue. All right. So this is one of the things that we have. So, for example, when doctors are using it, if they're treating a particular site which might be at a particular depth, and they know that that wavelength is going to get to that depth through that particular tissue, then they might have to up things like the amount of power, the width of the beam, because they want more light to get to that area, because they may be facing scattering on the pathway to the area where they're going to hit. And so it's a clinical thing. So everything is learned, if you get what I'm saying. It's learned with a little bit of trial and error. Medicine is never perfect, okay? Especially when using lasers. There is a general thing that you can do that will work. But every clinician I've known, all of these doctors who I've known who've been working with lasers for years, if I'm in a room with them and they're treating a patient, a new patient, you will hear them saying, I just want to try this, or I just want to test that. And that's because they're not going to take chances and make an assumption that this beam is going to make it, you know? So yes, absorption coefficients is very important depending on wavelength.
Thank you so much, Dr. Paul, for that answer. Very explanatory and quick to the point. So someone asked a question earlier, which I feel you've also answered, about knowing the different fields where lasers can be used. You've answered it in this just concluded session. But the second question to that part was, when we buy the different laser equipments, do the vendors provide some training on how to handle some minor issues? I know you've also explained like basic
Yes.
safety procedures, but do the
Yes.
vendors provide them?
Yeah. So typically, we found that if the vendors are dedicated laser suppliers, they will supply some training. One, they have to supply training. Remember this, they've got to supply training on how to use a laser.
Yeah.
That's a standard training, yeah? So the day when they come along and they put the laser together, maybe the day that they will also agree to say, we're going to show you how it works and how you can dial up the different values. And typically those guys who do that will have some idea of how some of the treatments can be done, okay? So they'll tell you, when you're using it at 100 milliwatts or you're using it at 2 joules, whatever it is, it will have this kind of effect. But there's normally an application specialist who is associated with a company. And that's what you might sometimes have to pay a bit extra to get that person in. But I would say that person is invaluable, because once they come along and show you what is needed, you'll have a good idea of how to use the laser. Not knowing how to use it at all is kind of terrible. So, and interestingly enough, we've had application specialists who've come in with fruit. They've come in with apples and oranges and pears. And the reason is, if you think of an orange, it's got a thicker skin, okay? It's got a skin which is about, say, 4 millimeters thick minimum, yeah? And then they have a pear, and a pear is like 1 millimeter to 1.5 millimeters thick. And then you have an apple, which is a little bit, it's kind of thin too, but it's not as soft as a pear. And then they fire the laser on it. They fire the laser on it and show you its actions. And what they're showing you is different skin. Because if you think about it, if you have a young person, their skin is going to be much more supple, more tight, yeah, and all the rest of it. And an older person's skin will be a little bit more worn, if you like, yeah? It's approaching much older leather, if you like, yeah? And so we'll have a different effect. And by using fruit, believe it or not, and firing on fruit, they get a good example of depth, how far down into the material that laser will go, right? They get an idea of how quick it is to burn, how wide is the field, and that's a very good training mechanism, I think. I thought when that application specialist, who was a doctor, yeah, she was a surgeon, plastic surgeon who is working for the company part-time and comes along and teaches. I was totally impressed that they would use that methodology to highlight what skin can be like. Yeah. There's also the application specialist who will agree to come with you on your first case when you're actually going to do somebody and will be there to guide you in doing that. Again, those are people you have to pay for. Yeah. They have the relevant experience and so on. Hospitals are a little bit different. If you're in a hospital and you have a surgeon who uses a laser before, the next best thing to do is to get in with him and be present during all his treatment. Because at some point when you're there, after a period of time, he's going to ask you to try. Yeah, because you've witnessed it, so try. And that's how doctors teach doctors. So if you're being taught by another doctor, that's perfect, because they're well on the way to seeing how things work. And I hope that answers the question. But yes, you do need an application specialist.
Thank you so much. So we now know that we need an application specialist. So
yes,
there's a question I asked. So what would be the responsibilities of medical physicists in lasers?
Laser
do we
safety,
do QAs, QCs? Like, what would be the role
that's
of
correct. So typically we do QCs. Yeah. All right. My service that I offer is a little bit different than most hospitals. Okay. And that's because we've been doing lasers for years. And we started out from the beginning. You know, I remember so many lasers that have come through my hospital have been prototypes. So we've had prototypes from Candela, Luminous, quite a few of the big companies. And we're still having prototypes coming in. And that's one of the reasons is, one is that they know we're very laser capable. And two, if they manage to get to say, Guy's and St. Thomas's uses it, it's almost a green light for every other hospital to use it. It's, oh, well, Guy's and St. Thomas's are using it. Because we're one of the first foundation trusts. We have a huge scientific background. We had one of the leading skin places, dermatology departments on the planet. It's called the St. John's Dermatology. It's the oldest hat. And these guys have been doing it from youngs. So we have guys who've worked in private sector that's come over to us. We've got a whole range. There's a series on telly. I don't know if you've ever seen it. It's called Bad Skin. You might, because I know it's international because I've seen it come up in other places. And it's a series about this doctor who's working in this private clinic, this lady, and she's treating all these skin complaints. And it's kind of gone global. She works for us. Yeah, she's one of our doctors, but she has a private clinic. So a lot of the doctors have their own private clinics. Yeah. And so as medical physics, what do we do? Well, we do our best to ensure, one, that these equipment are serviced. So in our medical physics section, we have a section known as clinical engineering, and clinical engineering ensures that every piece of kit we have in a trust has some kind of service contract. That's what we do. Two, as the laser people, we go along and we will QA them, make sure the QC is showing that this instrument is working within specification. We look at things like the eyewear, make sure that they're not broken, they don't have scratches and stuff like that. We give advice on their eyewear because we will do the calculations for them. We don't let the clinical staff do that. You can't just go and buy eyewear. We do the calculations and make sure that they get good eyewear. But we will offer them a range. So we can give them a range and say, which one do you like? Because you got to think of things like comfort. A doctor is going to be working. He's going to be working for like how many hours on a patient. You know, I've seen laser treatments where it's 600 shots, and each shot is like boom, boom, boom. So you think of the time that that doctor is going to be there. So you want to prevent things like eye strain. You don't want flashes that is just about normal for the eye, but enough to keep giving him a flash, he's going to have strain. And you don't want to do goggles which are just all wrapped like this, which is going to cause him to sweat on the inside and become uncomfortable. You want the clinician to be very comfortable in a good zone so that he gives the best treatment. Yeah. So there's things like that that we cover as medical physics. We kind of are in the background supporting and making sure everything goes smooth. We also put in place the local rules for them. We tend to write their local rules and their risk assessment. We go along, if they're going to use a room and it's the first time, we go along and make sure the room is acceptable. So if it's got windows, they got to put blinds in. So we get the works guys to come and put the blinds in. We'll put an adequate lock on the door. With theater environments, I don't like locks. Nurses have to go in and out. So we want the laser lights and signs to say, don't come in. There's laser procedure at the moment. But we want it so that the nurses can go in and out to go and get instruments that are not already in the theater. So you have to be practical and you have to develop a good working culture. And you help them by doing the training, laser safety training, warning them of all the issues that can happen. So everybody in the room have to have that training. That's medical physics. Yeah, and that's the support we give. We also give an additional support. Our additional support is we do a first point call. As engineers, we can do that. So they say, it's not working. You go along, you find out the doctor is not familiar with the kit. He's normally used to turning the key to turn it on and the laser work. Somebody switched it off at the back. Yeah. And this is when you get your revenge. You can toy with them. For example, I've been on calls where it's not working. And so I knew the switch was off at the back. So I hugged up the laser machine and I said, oh, please, I love you, laser. Please work for me. And I switched it on secretly. And then I turned it on with a key. And he was like, no, no, no. And so, it's bringing a laugh into your job. But you do things like that, But yes, so you got to get familiar with the kit, because sometimes you might have a new user and they're not too familiar. You got to help them out in that way. I hope that answers the question.
It does. Thank you so much. We know that we are currently out of your time, but would you be okay to
I'm all
still
right. I'm all right for
questions?
time. I'm okay for the rest of the day. So it's fine if you want to ask questions.
All right, sir. Thank you so much. So just a quick question. Are lasers used in radio diagnosis? And if yes, to what extent have they become used in radio diagnosis? Like, are they used in diagnosis of any kind of disease and radio diagnosis?
Absolutely, absolutely. So, so many lasers I've seen. So, Raman spectroscopy is one area. So, the Raman spectroscopy is when you use a one wavelength going in, and the material that it goes in, it shifts the spectrum when it's coming back out, which you then receive. Okay. And that can typically be used on your skin. It's going to be low-powered lasers, those. So they use that. There's one being built by this fellow who's working with the university at the moment, and they simply shine it on the inside of your jaw at the funny cells that they've been finding in there, and that quickly determines if the cells that are present there is cancerous, because once you chart things and get back their footprints, and light is brilliant for giving you footprints. Yeah. So if you want to use, say, a multi-wavelength thing, and you receive back the light, and laser light is effective in this because it's all coherent and it's going into the area. It's going to have a single effect. So you're not using this dispersed light, and it comes back and you read back the results, and you get a nice spectral footprint of it, what it's doing. Then you kind of see if it's different from the ordinary tissue which is there. So of course it's about collecting data. So first you collect data from normal, you collect data from disease, and you can then compare the two. Once you're looking for the footprint, then you can use it for diagnosis. Yeah. So yes, it's used like that. Where else is it used in terms of diagnosis? Response. So you may see something, you hit it, and you wait and see what the injury's healing response is. That's another way to diagnose, because you already know if it was normal skin, how it's going to heal. If it's abnormal skin, it's not going to heal normally. And so you're going to see that as well. So I think the uses for it is becoming more and more. But I would certainly say at the heart of it is Raman spectroscopy. And that's a separate physics, but it generally uses laser light. And that's a good way of doing diagnosis, but mainly on skin tissue.
Okay, so thank you so much for the answer. So we have a question that has arisen again. I mean, you talked about it briefly, but based on the question we asked during the poll session, which is, so does laser cause cancer?
Does lasers cause cancer?
Yeah.
So the only way a laser would cause cancer, right, is if you were to constantly expose yourself to a UV laser for a significant period of time. Yeah. Cancer is a strange one. Okay. So what we find with cancer cells is they take time to develop. So, for example, our biggest cancer-causing thing then that we use currently would be X-rays, okay, or the Linacs that treat cancers. That's the one thing. And what's the risk on that? It's really low. So a typical chest X-ray is equivalent to one transatlantic flight. So if you're flying from, say, Western Africa to the United States, that's equivalent to a chest X-ray in some cases. Yeah. How dangerous is radiation? Well, light radiation is going to certainly be so much less than X-ray, because X-rays are the ones that will do the damage. If you have the lower energy X-rays, they're going to be totally absorbed in there and they will look to cross. Remember, the reason why you will cause a cancer is because of a mutation. And the one way of getting a mutation is to disrupt the DNA. That's how you create it. By disrupting the DNA. You've got to disrupt the DNA in such a way that it doesn't repair itself. The DNA, when it repairs itself, doesn't repair itself accurately, so it does something wrong. And that's where you get your issue. So using lasers, typically day to day, will not give you cancer, no. I hope that answers it.
I think she's frozen.
Yes, I think
Yeah,
so
she's
too.
frozen. Okay, yes, but it answers it quite well.
Okay.
And it appears that when we did the poll, the ratio was 64% to 32%, or 64 to 36, which some people said yes, some people said no, that it couldn't cause cancer. So the way you've answered it also shows that probably we are in the right to think that it can cause cancer, but it's a very extreme case, from what I understand.
Yeah,
right?
it would. Yes, I will say it will not cause skin cancer. Not unless, just imagine, if you went for a set of treatments and say, typically there would be 6 treatments max in all, and you were being treated with an excimer laser, it would not be enough to cause cancer.
Okay.
So the only way it could cause cancer is you had some chemical in your body or on your body, and the light triggered it to do some kind of damaging thing. But no, it will not cause cancer. Do not believe it will cause cancer. Trust me. 25 years I've been with it, and I've not had any cancer. Let me touch some wood around here. I've not caused any cancer to myself using it.
Okay. So the correct answer should be no.
No.
Okay, thank you so much, Dr. Paul
Deacon-Smith.
Right. It's been an interesting conversation today on lasers. It's a whole new, different area of physics. I don't think there's a proper part of our curriculum that addresses lasers properly throughout our undergrad and postgraduate.
You're 100% right. You're 100% right.
Yeah,
so there is I'm just thinking, I will tell Ayabosa what I know, how to help you along you guys' way, yeah? So I think the first start is the MHRA document, which I will send to her, and hopefully she will dispatch to everybody. I think that's a good starting point. Another thing is, a lot of people don't examine stuff like the international organizations that we have. I'm always amazed by the information that you can glean from them. So, for example, working with radiation, the IAEA has lots of documents up there. I'm not quite sure if they covered anything on lasers. I can't remember looking about that. In terms of standards and information like that, it's normally ISO and British standards or American standards. So, and another thing is find the laser institutions. Go online and look up laser institutions. They always have a huge amount of documentation that you normally can download to look at. And so if you're setting up a service, there's lots of good hints through those organizations, how they did it and why they did it. And so we have to look at our international bodies because they generally are a really good source and they keep abreast of all the international agreements on what's best. And generally, medical associations are quite good at that. If you can find laser medical associations, that's quite good too, because they will have very good information on stuff like that as well. But I will certainly send the MHRA document through to ISO, and hopefully everybody will get a copy, because that's a good starting point.
Thank you so much, Dr. Paul.
It's been a pleasure.